Okay. Good evening, everyone. Am I audible?
Good evening. Yes, sir. Yeah.
Yeah. Okay. So, yeah, how many of you were from? Were present in my last live session? Some of you were present, right?
Yes, I was present.
Yes,
Voice is
sir.
very low.
Present,
Okay.
sir.
Okay. Good.
Your voice is
Yeah.
very low.
My voice is very low. Okay.
Yes.
Now is it okay? Little bit better.
Yes, sir. It seems to be better.
Okay. Good. Okay. So last time we discussed about axioms of vector space, basically a definition of vector space, and discuss about the subspace also. So, is there any doubt regarding that?
Your voice is not clear, sir.
Voice is not clear. Give me a minute. Okay?
Sir, mute everyone, sir.
Yeah. Now is it clear?
No,
How
sir.
about now?
No, sir.
Okay. Now?
Yes, sir. Now it's okay.
Okay. Yeah. Okay, so I was asking that is there any doubt in the definition of vector space and subspace? Is that clear? That part at least clear?
Yes, sir.
Okay. So if I want to, can you give me an example of a vector space? Anyone?
Line passing through origins.
Line passing through origin. So see, when you are saying an example of a vector space, you have to mention what are the operations you are doing there, right?
Yes, sir.
That I discussed, the last time. The operation is really important. So line passing through origin, and what are the operations there?
Usual addition and usual multiplication.
Okay, great. That is one example. Any other example?
Sir, your voice is echoing behind you.
Yes, sir. A little bit it is echoing and.
Is it for everyone?
Yes, sir.
Yeah, sir.
Hmm. Okay. So let me rejoin once, okay? Now can you hear me?
No, sir. Still same problem.
Yes, sir. Same problem.
Same problem, is it? I don't know why
Yes, sir.
it's happening.
Background noise, sir.
Some background noise and the mic seems to be more
too
close to
close.
your mouth.
Yes.
Mic is too much close to your mouth. It seems like this.
Okay, I will. Now?
Yeah.
Now,
Now it is okay.
it's better. It's better.
That's all I can do. I don't know how to manage it now.
Yes, yes. Now it's okay.
It's okay, sir.
Sir,
Okay.
what were you saying? Something important?
So I was saying that when you are giving some example of a vector space, it's
Now it
always, you have to mention what are the operations there, right? So as someone has already mentioned that a line passing through origin is an example of a vector space where the operation is basically usual addition and scalar multiplication.
Sir, could you please explain this point a little better about the usual multiplication or addition on the line passing through the origin and any others that
So
region?
usual addition and scalar multiplication means coordinate-wise addition, and scalar multiplication means coordinate-wise scalar multiplication.
That I understood, but the ones that fulfill those requirements or which have those operations, other than the line, the line passing through the origin, any other?
Deepa, were you present in my last lecture session?
Yes, sir, but I didn't
So I
understand
have-
on that day also.
Is it? Okay.
Yeah,
have
just
created-
if you could just explain this part about how do we
Which
realize,
part?
how do we know which addition or multiplication would it be the usual one or the
No,
special?
that will be given. That will be given in your question. Suppose I am asking you that whether this is a vector space or not,
Yes.
then the operation will be given along with the question.
Yes, but you're mentioning that for a line passing through the origin, we usually have the usual addition and multiplication.
No. That I am not saying. I am saying that when I am asking you to give an example of a vector space,
Yes.
now you are giving me a set. Now along with the set, you have to tell me what the operations there.
Okay. So we
Okay.
don't need to have examples of what would satisfy the usual addition and multiplication.
What does that mean?
No, I'm saying so we don't have to give examples of that, right? We will be given a set and we'll be told whether it's the usual addition or multiplication or some other different type, right?
See, I am saying two type of thing. So first of all, suppose I am giving you a set along with addition and scalar multiplication, and I am asking you whether this is a vector space or not. That is one type of question that we usually deal with.
Yes.
Another is that what just now I have asked, that tell me an example of a vector space. Now when I am asking you to tell me a vector space, you
Yes.
have to give me a set, you have to mention what are the operations there that you have to
Okay.
tell me. Okay,
Okay.
is it clear?
Yes, sir.
Sir, I
Okay.
have one question. In the
Yeah.
lecture for non-example of vector space, sir
Hmm.
has mentioned C of within brackets x1 comma x2 is equal to cx1 comma cx2. How is it? Can you explain on this, sir? It's not clear to me.
No, I mean, what is the set? What are the addition? This is only scalar multiplication. What is the set?
Yeah.
What was the set?
No, 1 second, sir. 1 second. I'll get you.
Yeah.
He has mentioned like non-example. Let us define addition and scalar multiplication in R2.
Okay, so
x1
set
comma
is
x2,
R2.
yeah, x1 comma x2 plus y1 comma y2 is equal to x1 plus y1 comma x2 minus y2. This is, it fails. I understood that one, addition.
So if addition fails, then there is no point of checking for scalar multiplication.
Okay, because, okay, fine.
I mean, you have to satisfy all the 8 axioms, no?
Okay, fine,
So,
yeah. Yes, sir. Okay, if addition passes, is the scalar
if
multiplication
addition passes,
pass?
then this is proper scalar multiplication. There is nothing wrong with it.
Okay, sir. Okay. I thought something is wrong in the second part also.
No.
Okay, sir. Thank you.
Sir, one
Yeah.
related question.
Yeah.
A bit I was confused. Sir, what to do when a condition is given that suppose it is R2 and vectors follow a condition. Suppose x plus 2y is equal to 0. So, what do we have to? Suppose we have to say see whether this is a vector space or not. First of all,
So
we
what is your
assume-
set? X comma y such that x plus y equal to 0. Is it? So you are saying about this set?
X plus 2y is
This-
equal to 0. X plus 2y is equal to 0.
Okay. Nothing special about this. Yeah.
Yeah. Sir, we have to check whether this is a vector space or not. Right.
Right.
What I am asking is we have to check it is closed on addition and scalar multiplication and all the 8 axioms.
So this is only the set. What are the addition and scalar multiplication? You have to tell me yet.
Okay.
So is the addition and scalar multiplication are the usual ones?
Yes, sir. They are the usual ones.
So once you know that those are the usual ones, so you already know they satisfy all the properties, right?
Yes, sir.
In R2.
Right.
Now this is a subset of R2, correct?
Okay. And
This
it
set
follows the
is a
standard
subset of
condition.
R2, is it correct?
Yes, sir.
So you only have to check whether this is a subspace or not. If it forms a subspace, then it's done, right?
So,
So
sir,
you
my
remember
question
I
here is,
mentioned 3 properties there.
suppose we have to check all the 8 axioms, right?
You don't
for
have to
the
check for 8 axiom. That's my point here.
yes, sir. What I am not getting here is what to do with this condition, sir. In some problems, this condition is given, like the set is elements of set follow this condition x plus 2y is equal to 0.
That's what I am saying. Suppose your addition is the usual one, and here this is scalar multiplication is the usual scalar multiplication. Okay, so this is the
Right.
set with operation given, and you are asked whether it is a vector space or not. Right? That is your question.
Yes, sir.
Right. Now, first you realize that this is a subset of R2, correct?
Yes, sir.
And R2 with usual addition and scalar multiplication is a vector space, correct?
Yes, sir. Correct.
So, if I consider V with this addition and scalar multiplication, and if I can show that V is a subspace, then we are done. Is it true?
Okay, then we have only to check whether it is a subspace of R2
Exactly. So, you have to check whether 0 is there or not. So, what is 0 here? Anyone can pitch in.
Yes, sir. 0 is there.
0, comma 0 belongs to this
Exactly.
vector space.
Exactly. So 0, comma 0 is in there. Yeah, right. And what about if I take two vectors from here? Is the addition lie in the same space in V?
Yes, sir.
Okay. So suppose I am taking x1, y1. So this is in V, and x2, y2. This is also in V. Okay. What about, so x1, y1 lies in V means what? x1 plus 2y1 is 0, correct? And here x2 plus 2y2 is 0, correct? That was the condition. Now if I add this to what I am getting, x1 plus x2, y1 plus y2, right? So this is the point I am getting after addition. So I have to show what about this thing?
Sir, x1 plus x2, 2y1 plus 2y2, no, sir?
No, this is addition only. You have to add this two point. This is usual addition. So what is the addition? x1 plus x2, y1 plus y2. That is your addition, right?
Yes, sir. Yes, sir.
So this is the point you are getting after adding. Now you have to check this condition whether this satisfies this condition or not. So now this is your x coordinate. This is your y coordinate. And the condition to be inside V is x plus 2y equal to 0. Right?
Right.
Yes, sir.
So you have to write this is your x, this is your y. So x plus 2y, whether it is 0 or not. Is it 0?
Yes, 0, sir.
It's 0, right?
X1
Because
plus
it
2y,
is x
yes.
plus 2y1. I can separate it.
Yes.
x2 plus 2y2.
x2 plus 2y2 will be 0.
This is 0.
This is 0.
So yeah, this addition is indeed close. Now third condition is scalar multiplication. So again you can check. So cxy. So this is your point cx comma cy. Now xy already belongs to V. That means x plus 2y is 0. Now what about this cx cy? So cx plus 2cy.
X plus 2cy.
So you can take c common, x plus 2y, and c into 0, that is 0. Correct?
Sir, in first line, x,
C into
comma
0.
y, they belong to R. Sir, in first line, they belong to V. Okay, sir. Right.
This is V. I mean, everything is inside R2, so I mean, all are real number. Right?
Sir, please don't erase it from the PDF.
Okay. I will not erase it. But have you understood it? I mean, is it clear?
Yes, sir. Yes, sir.
Yes,
Got the
sir.
point.
Yes,
Got the
sir.
point.
Okay, great.
Sir, if we have the line y is equal to mx plus c, would usual addition and multiplication apply to it?
I mean, usual addition and multiplication will apply to it, but it will not be a vector space. Can you tell me why?
Sorry? I
It
didn't
will
get
not be a vector space.
it would not fulfill, I suppose, the requirements that whatever we do after addition or multiplication, it would not fall within the.
I mean, more general thing you can say, I mean, more basic thing you can say in that line. Y equal to mx plus c, does it have a 0?
No, if c becomes 0, can we?
Only when c becomes 0.
Yes, yes. Okay.
Right?
Yeah.
Otherwise, 0, 0 will not satisfy that, right?
Yes.
So it will not be a vector space because 0 will not be there. This first condition will fail. Okay? And second and third will also fail, but okay, even the first one is failing, so we don't have to bother about that. Okay?
So that means for such a, when we're having a xy plane, this 0 vector would actually be 0, 0, not the other.
With respect to usual addition and scalar multiplication, if we change the addition and scalar multiplication, it will be different. Like earlier, I have given an example.
Okay. Yeah, now I get
Right.
it. Yeah, with usual addition and usual scalar multiplication, the 0 vector is actually 0, 0.
Exactly, right. I mean, that is the case, no? You can check it.
Yeah,
X
so
comma
it
y
will
plus
not-
something should be x comma y.
So 0,
So
0
that
would
should
not
be
lie on the that y is equal to mx plus c.
Exactly. So with respect to usual addition and scalar multiplication, that is not a vector space.
Thank you so much.
Okay? Yeah.
Got it.
Yeah. So hopefully this vector space subspace part is clear. You just revise it further once.
Excuse
So,
me, sir.
Yeah.
So did you upload the notes in the previous?
Yeah, I have uploaded that day only. That day itself I have uploaded.
Where? That's.
If you go to your portal and there is live session slides.
Sir, it is in supplementary content. Supplementary content.
You go inside supplementary content, there is a section called live session slides.
Okay.
Okay, so in that folder you can get all the notes. Okay, so now next part, basically we are going to say something about linear dependence and independence. So once you come inside a vector space, so you know you can do addition and you can do scalar multiplication. These two operations we have there. So if I have suppose n vectors or k vectors, as I have taken here k vectors, v1 to vk. Now I can write a linear combination about that. So what is a linear combination? Linear combination means I will use some scalars and I will use these vectors and I will add all these. Okay. So suppose I am getting, so v1 to vk is my vectors. So I am writing a1 v1 plus a2 v2 and so on to ak vk. Right? So this is basically a linear combination. So what does it mean? So a1, a2, ak, these are basically coming from real number, coming from the scalar. Okay, and I am doing scalar multiplication of ai with each vi and I am adding this. So this is basically called a linear combination. Okay, suppose I am giving you two vectors, 1, 3 and 2, 5. Okay, and suppose I am giving you two scalar. My a1 is 2, this is your v1, this is your v2, and now my a2 is 1. So can you tell me what will be the linear combination of these two vectors with respect to these two scalar with usual addition and scalar multiplication?
2, 6 plus.
So first is 2 into 1, 3 plus 1 into 2, 5. So this is 2, 6.
4, 8.
4, 8. No.
No, 11.
First one is 4, 11. Right. So basically I can see that this 4, 11 can be written as a linear combination of 1, 3 and 2, 5. Right?
Yes.
Right? Okay. Now, forget about this thing. I am adding one page here. Now suppose I have these two vectors 1, 0 and 0, 1. Okay. These two vectors you have seen at many places and you will be seeing in many places. So this is, I am calling it as my v1 and this is called v2. Now my question is, can we write any vector on R2 as a linear combination of these two vectors? So I am
Yes,
writing
sir.
the question.
Yes,
Can
sir.
we write?
Yes.
Yes, sir.
Yeah.
We can write.
How?
Taking
How we can
appropriate
write it?
coordinates.
A V1 plus B V2.
A1 and A2 is 1.
Not 1.
But we should get B1 and B2 also.
So A1 times of V1
A1 times
plus
of
V2
V1.
times of V2.
Yeah.
So any vector of R2 will be of the form this, right? A comma B, where A and B are any real number, right?
Yes.
So I can write A comma B as A into 1 comma 0 plus B into
B comma 0 comma 1.
Right? So any vector of R2 can be written as linear combination of these two vectors, correct?
Yes, sir.
Is this part clear at least?
Yes, sir.
Yes.
Okay.
Sir, how
Now,
do we be sure of this part? Like, this is where I'm confusing.
So any vector of R2 is of the form A comma B where A and B are any real number. This part is clear?
Yes, yes, sir.
So basically, if we take any A and any B, so if I want to give me a point, suppose you are giving me 7 comma 9. So what I will do? I will do 7 into 1 comma 0 and 9 into 0 comma 1. Right? So if you give me any vector, I can just multiply the first coordinate with 1 comma 0 and the second coordinate with the second
0
vector.
comma 1.
0 comma 1. And I am getting the same thing. Right?
Okay.
Yes, sir.
Clear, no?
So here, like, I understood, but like in bigger vectors, it becomes confusing later.
Not bigger vector, you say you are going to say in higher dimension, is it?
Yes, yes, sorry, sir.
I will come to that.
Okay.
So higher dimension also come to that, but try to visualize what is happening here. So xy plane means this is my R2. So 1 comma 0 vector is somewhere here, right? And here is my 0 comma 1 vector, right? These two vectors I am talking about. Now when I am multiplying this with some, suppose you want to write this point, whatever this point may be. How we will get this point? So this is 1, suppose this is my A comma B. Or say take a particular point, say 4 comma 5 comma 4. So what we will do? You will take, this is 1, this is 2 comma 0, this is 3 comma 0, 4 comma 0, 5 comma 0. Like somewhere you come to 5 comma 0. So in this direction, you are basically multiplying this with 5. You are taking 5 times, right? To get here. Similarly, in this side, you are getting 4 times to get here, 0 comma 4. And this point is your 5 comma 4, correct? That is what you are doing.
Sir, 5 comma 4 is a vector in vector space.
Yeah, 5 comma 4 is in R2. So here my vector space is R2 with usual addition and scalar multiplication. Okay?
Okay, sir.
Okay, so basically what we are doing, we can express any point on x-axis by 1 comma 0 by just taking scalar multiplication. We can take any point on y-axis by scalar multiplication of 0 comma 1, and once I get these 2 points, I can definitely get any point on xy plane. Is it clear? I mean, that is basic coordinate geometry. Right?
Clear.
Yes.
This is clear, right?
Yes.
Okay. But why this is important? Why are we doing this? Is there something special about 0 comma 1 and 1 comma 0? There is x-axis and y-axis. But suppose I am changing it to some other thing. 1 comma 0 I remain as it is. The second thing I am changing as 1 comma 1. Now can we do that? The same thing?
No.
Are you sure?
We can do it,
Think
but
a
it
little
will be a
bit.
different line.
Exactly. It will be a different line. The second vector will not generate y-axis. It will generate some different line.
Yes.
Now how we can do it? So what we want to do here? We want to express a comma b in terms of 1 comma 0 and 1 comma 1, right? So Basically, I want to find this x and y. Right? I want to find this x and y so that this equation satisfies. Right? So what is this? A comma b is x comma 0 plus y comma y. So that means a comma b is x plus y and y. So what are the equations I am getting from here? I am getting two equations. X plus y is a and y is b. So can you see there? This is a system of linear equation, right? Which we have studied in first 2 weeks.
Yes, yes.
And there is a connection between these two. Right? Yes. This is the connecting point. I want to write some vector as a linear combination of some other vectors. How can you write it? Basically, I have to solve for the coefficient, this coefficient. What I have written as x and y here. You can take C1, C2, whatever you want. That is just the notation. Now you write this equation. You equate each coordinate with that one. And you will come up to a system of linear equation. And you have to solve it, right, to find x and y. If you can find x and y, then yes, you can write it. If you cannot find, then yeah, you cannot do it. Right? So that is the main motivation here. Is it clear to everybody?
So this
now what I have said?
We can row reduction and all we can do.
The process you know, but I am asking about whether the motivation is clear, what we are trying to do.
Okay. How we arrive at a linear equation.
Exactly, how we are arriving at a linear equation.
Okay.
So why this is important? Why this, solving this linear combination, finding the linear combination. Basically, we are trying to solve a linear equation, set of linear equations. Right? We are doing nothing fancy here. Okay? Is it clear to everyone?
Yes, sir.
Okay? Okay. Because that will eventually boils down to linear dependence and independent. So how we will go there, I will show you. So can you tell me the solution of x and y in this case at least?
X equals to a minus y, y equals to
So y equal to b and x equal to a minus b. Right? Okay. So is the solution unique?
Yeah, unique.
Solution is unique, right?
Yes, yes.
How you can know, you can get it?
Sir, x value is depend on b.
But for now, assume that AB is fixed. Some
B
fixed
changes,
AB.
then a minus b changes, and then y it is.
But now assume that AB is fixed. You don't have to worry about A and B.
Then unique.
Then it is unique. What are the ways you can tell that this is unique? How you can find it?
It's not 0,
By
0.
seeing the linear equation, you can tell it, right?
Yes.
How?
X plus y is not equal to 0 means it is not 0, 0.
No. Anyone else? What is the matrix equation of this system?
1, 1.
If it's invertible, then
1, 1, 0, 1.
Sir, 1, 0, 1, 1.
So this is the coefficient matrix, right?
Yes.
Yes.
And coefficient matrix is invertible. The determinant is non-zero, right?
Yeah.
yes.
Correct?
And we have
That's why you can say that this solution is unique because this matrix is invertible. Correct?
Yeah, determinant is non-zero. Correct.
Now can you observe that this first column is basically your first vector and second column is basically your second vector.
Yes, sir.
Right?
Yes, sir.
So something is going on here.
So how is the determinant not 0?
No.
What is its determinant?
1.
Hey, who is this? Who is asking determinant is why this is not 0? What is the determinant of this matrix?
It should be 1. Sorry.
So non-zero, no?
1 minus 0 equal to 1.
So 1 into 1 minus 1 into 0. So determinant is 1. So which is non-zero. Right? So this matrix is invertible. Correct?
Yes.
Yes.
Okay. And I am seeing that basically these two vectors which I have started with, that is coming as the column of this matrix. Right?
Yes.
So this is basically the case which is going here. Once I want to write any vector as a linear combination of this, and I am asking whether I can write it or not. So it boils down to solving this coefficient, which I have mentioned it as x and y. From that I can get a system of linear equation. Now once I get a system of linear equation, I know how to find the matrix, coefficient matrix from there. Now depending on the coefficient matrix, I can tell whether I have a unique solution or no solution.
No solution.
Right? Or infinitely many solutions, that also possible. Right?
Here I have one doubt, sir.
Yeah.
Here we have V1, V2, V3. Okay, so we will take the same example, V1, V2. It is always a rule that V1, that it will be column vertical.
Right. It will be column. Because you see what I have done here, it will become as a column.
It will be column. Okay.
Yeah.
Because I had a doubt whether I have to write it in row wise or column wise. Now it is clear.
Yeah. Okay. So this is what we have. So what about this? So any vector can R2 can be written as linear combination of 1, 0 and 1, 1.
Yes.
Yes, you can write.
Yes, right? You can write it. Right? Suppose I am giving you 7, 6. What will be your coefficient? How we can write 7, 6?
Even 1, 6. 1 and 6.
1 into 1, 0.
This is 1 and this is
and that
6.
will be 6. Yeah.
Right? Yeah. So this is how we can find the coefficient. Okay. Now I will go little bit further.
Sir, is it the only method of finding the coefficients?
For finding the coefficient, it is the only method.
So here, how did you get?
I mean, you have to solve linear system equation somewhere. That is the way.
Sir, right.
Yeah.
Sir, here.
Sir, if 7 and 6 is given, and if I take coefficient as A and B, and we solve the equation,
then you will get.
You can get A and B.
That is what I am doing, no?
So here to find the coefficients multiple times we have to try, right? Trial and error method. We get the coefficients.
No, where I am trying trial and error method? I am solving the equation, no?
The last
so
line.
Here A is, what is A? A is 7, B is 6, right?
Yeah.
So 1 plus
So what is the solution? Y equal to 6 and x equal to 7 minus 6, 1.
You are substituting in the expression, right?
Right.
Right.
So that I did it for general. Now I am asking you to find for 7, 6.
So we have done this to find the coefficients.
Then they can directly solve in this way.
One by one. Yeah.
Excuse me, sir.
Yeah.
So in this question, you have taken x and y to find the coefficients only.
Right.
X and y equals to and y equals to b. Whenever we want to find the coefficient, then we have to solve like this. First, we will make a linear equation.
Exactly.
Then after
Exactly.
Okay, thank you, sir.
So from this, if you give any pair, we can conclude that the given pair is a linear combination or not, right, sir?
I will show where not I have not shown yet. Till now I have shown that it can be written, but there is a point where we cannot. That I will come later.
And so in the previous example you have taken, you have coefficients there.
Yeah.
As if you have done exactly A and B here. Then you have taken
this is a lot more easier, no? If we want to write A comma B as this, the same thing you can write. So what is coming here? A comma B is x comma 0 plus 0 comma y. So this is x comma y. So your equation is basically x equal to A and y equal to B. So that is exactly your solution. Nothing special going on there.
Okay,
right?
Thank you.
Here what is your matrix? Your matrix was this.
Yes, sir.
Identity matrix.
I have a question.
Yeah.
Yes.
Yeah.
Yeah. A question is essentially this is a regular vector which is having x and y. If I have a 2 by 2 matrix as a vector, then can I?
I will come to that later.
Okay.
2 by 2. Let's finish this portion first, then I will come. That is exactly the same process, but you have to do it little more carefully. Nothing else.
Okay.
If you understand this, you can do this.
So, sir, here all the pairs. So can you mute? So all the pairs that you represent in the form of A comma B will form a vector space or subspace of a vectors.
No, A comma B I am taking from R2 itself.
Yes,
so
sir.
This is any point of R2. So my point was
all those set form a vector space, right?
R2 is a vector space, no?
Then
R2
A
itself
comma
is
B.
a vector space.
Okay, A comma B belongs to R2. Then the pairs which satisfy this condition
Which
belongs
condition?
to
I have not given any condition.
x plus y comma y.
No, that is not condition. See what I was doing. I am taking any point A comma B from R2. No condition, okay? Any point. Now I am asking whether I can write A comma B as a linear combination of V1 and V2. That was my question. And the answer
V1
is yes.
Sir, V1 and V2 is already given.
Already given.
V1 and V2 could be any vector.
I can change it. I will change it in the next example. So that was the question. There is no condition and nothing else. Okay.
And we will have to check whether it forms a linear combination or not.
Exactly. That was the question.
And there are three things that are given. I am giving a vector A comma B, vector V1 and vector V2. And we have to check whether the two vectors make a linear combination with A comma B.
I mean, by taking linear combination of V1 and V2, can we represent A comma B?
So here linear combination. Okay, continue. Sorry, continue.
The physical meaning of a complete problem is that whether we can combine V1 and V2 and form another vector that is A comma B.
Exactly.
Yes, sir, got it.
Yeah.
So here linear combination means all everything should lie in the same line, right, sir?
No, that is not. Linear combination means you just scalar multiple, take a scalar, multiply with the vector V1, take another scalar, multiply with the vector V2, and add those two. By doing that, can you get A comma B?
Okay. That should be in vector space.
Sir?
Everything is going inside a vector space now. Okay.
Sir, I have a small question here. Like, sure, the vector 1 is 1, 0 and vector 2 is 1, 1. That will be given in the question, and AB point will be given to us, and it will be asked whether that point AB can I represent using this V1 and V2, right?
Exactly.
But also you explained about the AB, the point, and which includes x comma 0, 0 comma y. Through that also I can represent my vectors, right? That point. But how do we know that which one we need to use? Whether it will be mentioned that you need to use x comma 0.
V1 and V2 will be given. No? That's the point.
Sir, can we say that we are studying generalized vector addition?
No, we are not doing anything generalized. We are doing whatever vector addition we know. See, okay, I will revise what I have said. Okay.
Sir, is there any combination for generating?
No, I am making a summary. Then you can ask again. Okay.
Yeah.
Give me.
Yes, sir.
Okay. So what I was doing in the previous page, you know R2 with usual addition and scalar multiplication is a vector space. That we know. Right. So inside this vector space, there are set of points like A comma B. All the points are basically of the form A comma B. Now, if you give me any point A comma B, this is a general point. Any point. A and B can take any real values. First question was, I am giving you a set V1, V2, where V1 is, that is the first question, first example, 0, 1. So V1 is 1, 0 and V2 is 0, 1. My question was, can I express A, B as a linear combination of V1 and V2? That means, can I write A, B as a linear combination? Is there any C1 and C2 such that I can write this? The answer was, yes, I can. In that case, C1 is A and C2 is B. How I get it?
B.
Let me finish, then you can ask. Okay. So C1 is A and C2 is B. Now the second question is, the setup is same. R2 is the vector space. I am taking any point A comma B. Now I change in my set. I am giving me another set S prime, where V1, V2. In this case, V1 was 1 comma 0 and V2 is 1 comma 1. Question was saying, can I represent A comma B such that this happen? I mean, I can write it as linear combination of 1 comma 0 and 1 comma 1. So in that case also, using system of linear equation, solving system of linear equation, we got that C1 was A minus B and C2 was B. Basically, we can. Again, we can, and the solution is unique. This C1 and C2 was unique. And we can write any point on R2 as a linear combination of these two vectors. Is it clear? Now you can ask if you have any doubt.
Then all points in R2 can be represented using a collinear combination of vectors, right, sir?
Yeah, don't say collinear, linear combination. Okay, because these 2 points are not on same line.
Yeah.
So it's a linear combination.
Linear combination.
Yeah.
Sir, if A and B are non-zero, then only we can say that it is a linear combination.
No, why? If it is not, I mean, even if it is 0, what is the problem? Your C1 and C2 will be 0 comma 0, no?
Then all will be 0, na?
So what is the problem? That is a linear combination, no? C1 and C2 can be 0. It is a real number. It can be 0.
That means if I want to generate a linear combination from two vectors, then there is no condition. We just simply multiply and add.
Exactly. With any real number. It can be 0 also. Okay. Is it clear?
Sir, how did you get that C1 is equal to A minus B, C2 is equal to B?
Have you joined just now?
No. I just
This
lost
one,
the
no?
track.
Okay, this one, the solving system of linear equation.
Yeah. Okay, fine. Thank you.
Okay. So if you write it as what you will get? You will get C1 plus C2 for the first coordinate and C2 for the second coordinate. So C1 plus C2 will be A and C2 will be B. Now if you solve this for C1 and C2, we will get the solution, right?
Yeah. Thank you.
Okay, good. Any other doubt till this point?
No, sir. You can.
So this is the first basic step about the linear combination. What a linear combination is and how it is related to system of linear equation. This is the basic step. Yeah.
I just got confused. So here AB is the vector, right? And V1 and V2 are given vectors. We are checking whether AB is the linear with these two or not. We are checking this.
No, we are writing whether AB is a linear combination of V1 and V2. Okay.
So for this we are finding coefficients.
Actually, so basically, my question was whether I can write AB as a linear combination of V1 and V2. So let me write the question. Can we write A comma B as a linear combination of V1 and V2? These are given. AB is also given. Okay.
Yes.
That was my question. So what does it mean? Whether we can find any C1 and C2 like this, so that I can write this equation.
So we can state it like we are given two vectors V1 and V2, and we are making a linear expansion of two vectors, and we are checking whether they add up or not.
Add up to give that result.
A particular result or not.
Right. That is the thing.
So then for all the points, for any A comma B, there will exist a linear combination, right? So the answer is always yes.
In this case, it is always yes, but I am going to show that answer is not always yes.
Sir, in this case,
that depends on the vector V1 and V2. Okay.
Sir, if in this case C1, C2 is 0, then it is not linearly connected.
Why? No. This is linearly independent.
Then the value of C1 is 0, then 7 is equal to 0 or something. Then it is
No. So that depends on the point. I mean, okay. If 7, 6, then the C1 and C2 are unique. You have already proved that, right? You proved that this solution is unique, right? For any A, B. Correct? Now, if A, B is 7, 6, 1 minute. Now, if A, B is 7, 6, your solutions are unique, right? The solution for C1 and C2 are unique, right? Do you agree?
Yeah.
Yes, why?
So if we fail to find C1 and C2?
No, that was not my question. I am asking for any A, B, the solution of C1 and C2 are unique. Do you agree to this?
Yes, sir.
Why?
Because C1 is equal to A minus B.
That is coming later.
Because determinant is not equal to 0.
Exactly. The system of linear equation which we are getting from this, the coefficient matrix was invertible. That's why the solution is unique, right? Yes. So when your A is 7 and B is 6, you know the solution is unique and the solution is 1 and 6, right? Now someone is asking that C1 and C2 can be 0 or not. If your this given vector 7, 6, if that is given, then you know solution is only 1, 6. I mean 1 and 6. There is no other solution. Now when C1 and C2 both are 0, what is your A, B can be? Both should be 0.
Both should be 0, yes.
Sir, 1, 6, we find 1, 6 or it is given that it is 1, 6?
Oh, you are asking it now after so long discussion. That's how we find the solution, no? C1 plus C2 is A and C2 is B. If you solve the system of linear equation,
we get 1, 6.
So that is what we got. Right? Is it clear?
Yes, sir.
Yes, sir. After that matrix you got no 1, 1, 0, 1, but the equation is 1, 2, 1, 1. So is it like how did you get that this matrix?
This is the coefficient matrix, huh?
So in the equation it is 1, 0 and 1, 1, right? How did we get this?
So writing this as column that I said.
Sir, so the coefficient matrix will not always give a unique solution, no?
That in that case scenario I will come later. But at least for in this case, have you understood that this is giving a unique solution, and that's why this 1 and 6 are fixed for this vector 7, 6.
For given vector v1 and v2, we get a unique solution.
Right. For given vector v1 and v2, we get a unique solution for any AB.
For any AB, yes, sir.
Yes.
Is it clear?
Yes, sir. For different vectors, the solutions may vary.
May vary. I will come to that. Okay. Now, my second question is, I mean, some of you are asking this. When C1 and C2 are 0?
So when linear equation is
homogeneous, 7, 6 value will be
linear independent, then C1.
No, don't go to linear independent. I have not mentioned linear independent till now. Just answer what I am telling you now. Just answer based on that. Okay.
The linear equation is homogeneous.
Linear equation is homogeneous, and in that case, if C1 and C2 both are 0, this A, B must be 0, 0, right?
Yes.
And that is basically your system of homogeneous equation. Right? Clear?
Yes.
Is it clear?
Yes,
sir.
I cannot recall the system of homogeneous.
System of homogeneous equation means in this portion, the Ax, B, this B is 0.
B will be 0.
Just remember the augmented
Constant
matrix.
term was 0.
Constant term is 0.
Also, can you explain linear independence or linear dependence also once?
I haven't explained it at all, so I will come to that.
Okay.
That will be much delayed because I have to go through all this. Okay.
One thing I have to discuss. Hello.
Yeah.
Sometime in the activity question, instead of value in the vector, there is pi and e mentioned. Please solve.
That is also value, no? Pi and e is also value. Pi is a real number, right? So that is a value.
If you
E
please
is also a real
solve
number.
any example using pi n.
That is nothing special there, pi and e. Those are also real number. Nothing special
We
in
just
those.
directly put the value like pi is equal to 3.14
You
and
don't
so.
need that. You don't need that for those questions. Okay. Just think of that question. You don't need what is the value of pi or what is the value of e for that solving that question. Okay. Okay. So now if you still have doubt on this question, you can post it in discourse. Okay. Or after the session, I will discuss that. So till this point, do you have any doubt?
No,
Anyone?
sir.
No,
No,
sir.
sir.
No, sir.
Why I
You can
am
move
moving
further.
ahead. Okay.
No, sir.
Okay. Okay. So now suppose I am giving you the set as 1 comma not 1 comma 0, say 3 comma 5 and say 9 comma 15. Okay. Now I am asking the same question. In R2, I have given you any vector a comma b. Can you solve this system of linear equation? I mean, can you write a comma b as a linear combination of these two vectors? That is the question, right? So what is the next step? The same thing what we are doing earlier.
A is equal to 3C1
3C1,
plus
Answer to first
5C1
9C2.
plus
answer to first
9C2,
question is yes,
15C2.
because 9 comma 50 is a multiple of 3 comma 5.
If you know this, then it is okay, but let me try to find it.
Yes,
Okay.
sir. Yes, sir. Yes, sir.
Okay. So a comma b is
That should be comma, right?
3C1 plus
9C2 comma 15.
right. Sorry. C2 comma 5C1 plus 15C2. Correct?
Yes.
So 3C1 plus 9C2 equal to
Equal
some
to
value A.
Sir, this C1,
5C1.
C2 is just X and Y, right?
I mean any variable. So I am taking C1, C2.
Okay.
You can write it X and Y, no issue.
So I think no solution for this.
So in this case, C1 and C2 are 1.
No solution.
You are saying C1, C2 is 1. Is it?
In this case, C1 and C2, the coefficient of 1 or other value.
Why 1?
But as
I mean, we are trying to find the value, whether C1, C2 exist or not. That is my question, right?
no solution because determinant is 0.
Sir, here the determinant is 0.
So basically, I have to solve this system of linear equation. I am getting this coefficient matrix. And what is the determinant? Determinant is 0. So matrix is
It's not
invertible.
unique. Invertible.
So matrix, the value is not unique. But is there any value at all?
Sir,
No value.
Last question.
No value.
No value. Why?
Because if you simplify the determinant, we can get 1, 3 and 1, 3 and here a by 3 and b by 5. If you convert it to augmented matrix. If we convert this in augmented matrix, then we can divide it 1.
So let me write the augmented matrix as you are saying. Yes. Then what I have to do?
Now,
then divide first row by 3, second row by 5.
Okay, first row by 3.
And second row
sir,
by
we
5.
could use RREF
So I am dividing second row by 5.
method, right?
Then?
And now R1 minus R2.
So this is R1 by 3, this is R2 by 5, and this is 5, this is 5.
By 5.
And
now
then?
R1 minus R2. Or R2 minus R1 is both are same. And now 0 is equal to a by 5. There is
So no solution.
Always no solution?
Yes.
Sir, it has a solution if A and B are 0.
Not always, sir. Either it can be infinitely many solutions.
No, infinite solution, yes.
That depends on A and B, right? Can you see that?
Yes,
sir. It depends on this. If this is non-zero, if this is non-zero, then no solution, right? If this is 0, then infinitely many solution.
Yes, sir.
Right?
Yes.
Is it clear to everyone? I mean,
Sir,
this is week 1, 2, right?
excuse me, sir.
Yeah.
Sir, we can also directly write the matrix, sir, because the vector is in the matrix, it's becoming the column vector.
Right. That I have already mentioned, but I want to show you how the vector actually it is coming, right?
Okay.
So I have already mentioned it basically. So if you can see this 3, 5, that basically your column, first
Yes,
column.
sir. Yes.
And this 9, 5, that is basically your second column, right? Yeah. So no issues there. So my point is, this system of linear equation has no solution if b by 5 minus a by 3 is non-zero, and b by 5 minus a by 3 is 0, then there are infinitely many solutions, right? Right?
Right.
Sir, but we will have to check now whether it is whether there is a no solution or infinitely many solutions.
That is what I have written. No? If it is non-zero, then there is no solution. If it is 0, then there is infinite many.
Yes, sir.
Right?
But we cannot determine it by here only. That if the
no, it is determined already. No, what else you have to determine here?
No, sir. In that place, that determinant is 0. Then we cannot directly say that the
from there itself we cannot say, right?
Yeah.
Right.
We will have
from
to
the coefficient matrix we
there.
cannot say. We have to create the augmented matrix and solve it. Basically, we have to solve the system of linear equation. That's my point.
Yes.
Okay.
Yes.
Whatever that means.
But as of now, we are having infinitely many solutions, sir, right?
If b by 5 minus a by 3 is 0, then infinitely many solution. If it is non-zero, then no solution. Right?
Yes. We have to use the row echelon form when this is not a homogeneous system of equations. Right? If it had been a homogeneous system, then we would have derived from the determinant only.
Right. Okay. Till now, this is clear?
Yes, sir. One more example. Okay.
I will do, but it is not finished yet.
Okay.
Yeah. So what I am getting here is these two conditions. So let me go to the second condition first, where there are infinitely many solutions. What does it mean? So my solution was b by 5 minus a by 3 equal to 0. So from here I can write is 3b minus 5a equal to 0. That means 5a equal to 3b. This type of points, right? Or 5a minus 3b equal to 0. This point, this line basically. Right? If I have this condition, then you can say that there are infinitely many solutions. Now, is this true? What are the vectors? Vector was 3, 5, 9, 15. 3, 5, 9, 15. So what is happening there actually? Why for this type of point there are infinitely many solutions? Can someone seeing anything here?
It is thrice the other vector.
They are multiples of each other.
So the second vector is 3 times the first vector. That is okay. But why this type of point have infinitely many solutions?
So it depends on D and
The intersection is
We represent the same line.
Because linear combination will form a straight line.
The lines
basically what is happening here?
The lines are parallel in one case, the lines are overlapping in the other case.
Yes.
These are dependent. So A and B are dependent, na? That is why.
But I have not mentioned what dependency is. Okay. So by just this point, I am asking, have you understood my question? I am asking why this type of point, I mean why this a comma b such that 5a equal to 3b. Why this type of points have infinitely many ways I can express as a linear combination of these two. Can you tell me?
Because
They are lying
these
on
two
the same
vectors
line.
are not linear
Because they are
combination
same
of
line.
A and B.
Same line.
Because
So it is
A
depends
is
on B.
So
because
exactly.
because
Suppose,
these lines are scaled.
Exactly. So that is basically all these vectors lying on the same line, joining this 0, 0 and 3, 5, 9, 15, all are on the same line, right?
Yeah.
And we can go on.
So line is basically A equal to 3 by 5b. So basically x equal to 3 by 5y, this line. All the points on this line
X can be
this set will be on this
the
set.
multiple of
Correct? Huh?
Will
because,
be
because y
every
can be represented as a multiple of x.
That is okay. So this is the line we are talking about, and all the points on this line can be written as a linear combination of these two, and there are infinitely many ways in which we can do that, right? So can you tell me any point on this line other than these two? These 2 points are on this line, right? Other than these 2 points,
we can keep
any
putting the
point.
value of y and we get keep getting
6,
12,
20.
10.
6, 10.
Huh?
12, 20.
12, 20. I have heard 12, 20. Okay, fine. 12,
6,
20.
10. 6, 10.
Okay. I will start with 12, 20. Tell me a combination. Tell me a combination. What is the coefficient? What are the coefficients?
1, 1.
1, 1.
1, 1. Is there any other? Is there any other?
No, sir, it's a unique solution.
No, sir.
No, it's not unique. These are infinitely many. There are many other.
4, 0, 0. Sir, 4, 0.
So yeah, put 1, 0 and take this.
Yes, yes.
Yes.
Okay. There are infinitely many, right? Can you see now that there are infinitely many ways we can do that?
Yes. Yes.
Right?
Yeah. We can put first 0, 0 and then 4 by 3 on the second.
Also, sir, minus.
Also, sir, 0 and 4 by 3.
Anything. And where are the solution coming from?
0, 0, sir.
This one.
How 0, 0?
C1 plus 3C2 is A by 3.
Because it is passing from origin, na?
0, 0 is a point on this line. Okay. So C1 here, when I am solving this equation, if this portion is 0, which case we are talking about, for which case we are getting infinitely many solution. So this portion is 0, right? So what I have left with C1 plus 3C2 equal to A by 3, right? C1 plus 3C2 is A by 3, right?
Yes, sir.
Yes.
So basically, what I am getting C1 is A by 3 minus 3C2. Now I have given you 12, 20. What is A? A is 12 here, right? So in this case, this is 4 minus C2. Now whatever value we take for C2, 4 minus C2 will be value for C1. Suppose I wish to take C2 as 5. Okay. My C1 value would be, this is what? 15 minus 11, I think. That will again give you 12, 20. So you change the value of C2, you will get defined values for C1. Right? That we have already derived. Is it clear?
Okay.
Yes, sir.
Yes, sir.
Okay. Okay. So this is the case. So basically, why this happened because these two vectors which we have started with, these two are basically on the same line, joining the origin. If we draw a line from origin connecting 3, 5, it will also touch 9, 15. Right? Basically 9, 15 it itself is scalar multiple of 3, 5. Right? Now, any point which is not on this line, any point which is not on this line, can we express that as a linear combination of these two vectors?
No, sir.
Yes, sir.
Yes, sir.
No.
Yes, sir.
No. Why? How? Someone is saying yes. She has to tell me how we can do that.
No, sir. No.
Why you think that it can be done? I mean, then I can understand where you are thinking wrong.
Now you must be confused. If we have another point, then we can form any vector in R2 with those vectors.
See, any point which is not on this line, for that point, this v by 5 minus a by 3 is non-zero, right? So there is 0 equal to some non-zero term is coming, which is absurd. So basically there is no solution for this system. So I really cannot find any C1 and C2. Okay? Suppose I am giving you 1,
Sir, in
0.
that case, where there is no solution, then can we say that they are not linear combinations?
That point is not a linear combination of these 2 points. Exactly.
Sir, what if this line is the resultant of addition of parallelogram, law of addition of everything?
No, first day I have said don't go to parallelogram law, addition, physics concept here. If you try to derive it everywhere you are seeing this, then you will be more confused. Think it as a point here. Okay. I have said that what is this one? So this one is basically if we join 0, 0 with any of these 2 vectors, then the second vector will lie on that same line. Okay, that is part is clear, right? That these 2 points are basically lying on x equal to 3 by 5 1 line, right? This part is
Sir,
clear.
and suppose if we don't have any solution for that particular vector, then is it possible to graphically present it?
I am presenting it. See, suppose I am trying to show that 1, 0. I am asking you 1, 0. Can we write 1, 0 as a linear combination of these 2?
No, sir, I don't think so.
No, right?
Yeah.
Because if we try to solve this, we will get stuck that this 0 equal to something will come here which is non-zero. So this system of linear equation we cannot solve really. Okay? So there is no solution for C1 and C2. So where this point actually lies? So I am saying this is my origin. If you draw this line, here somewhere 3, 5 lies. Here somewhere 9, 15 lies. And this line is x equal to 3 by 5y. Right? All the points of this line can be expressed as a linear combination of these 2 points. That part is clear, really clear. Because that is itself a vector subspace. Right? Any other point. So where is 1, 0? 1, 0 is somewhere here, which is outside this line. Any other point which is not on this line cannot be written as a linear combination of these 2 vectors. Clear?
Sir, but in the last example, the points were on different, right, sir?
So for the last 2 vector, what happened?
But that
These
was
two.
a unique solution, na?
Where was 1, 0? This is 1, 0, right?
Yeah.
And where is 1, 1? This is 1, 1.
Yeah.
Right? Now if you join 0, 0 with one of the point, is the other point lying on the same line? No, right? There are 2 lines. These 2 lines. Right?
Sir, can we say that?
So that is why I said when you asked other points can be a linear combination of this line, something you asked me, no?
But in this case it is not, right? These are 2 points. 3, 5 and 9, 15. 1 minute. 3, 5 and 9, 15, right?
Sir, you can show her,
and all these 1 minute. 1 minute.
I'm confused.
If you join this 0, 0 with one of this point and it is passing through the next point also 9, 15, right? And all the points of this line, only those points can be expressed as a linear combination of these 2 vectors. But what was in the earlier case, this is your 1, 0 and this is your 1, 1, right? These are 2 different lines. Okay? Is it clear?
Yes, sir.
Yes,
I'm
sir.
confused.
Actually,
Yes, sir.
9,
What was your
15
confusion?
is a
Sir,
scalar
you can
multiplication.
you
I
can
thought
show her
any
in the
point,
previous.
no, I thought any point can be expressed as a linear combination of other 2 vectors.
That is not always true. That is the point of this
Any 2
example.
vectors.
That is not always true.
Okay.
That's what we are doing throughout this example, right? I am giving you 2 points. There are some points which cannot be written as linear combination of these 2 vectors, right?
Yes, sir.
Basically, what you have to do, you have to, you tell what you are telling.
can we say that if we join 2 points with origin and they are non-collinear, then we can express any point.
Exactly. Okay. Yeah. So basically, what you have to do when you are trying to express some point as a linear combination of other two vectors or other 2 points. So I am writing the system of linear equation. If the system of linear equation have a unique solution, then it's okay. Then it's fine. There is a solution for C1 and C2, and we can express that point as a linear combination of those two, right? But in this case, we are seeing that in some cases there are no solution at all. So we really cannot find the coefficient, right?
Yes, sir. Got it.
Got it, no?
Yes, sir. Yes, sir.
So in this case only.
So in earlier case there was only one solution, but in this case there are infinite solutions.
Infinitely many solutions for some points and no solution for other points. For those points which have infinitely many solutions, those can be written, and only those points can be written. Other than that, no point can be written as a linear combination. Is it clear?
Yes, sir.
Yes.
So there are 3 cases. When there is a unique solution, then it can be written. When there are infinitely many solutions, then also those points can be written. But if there is no solution, then you cannot write it. Basically, that was the point of discussing all this, right?
Yes, sir. Got
Clear?
it. Yes, sir.
Okay. Any other doubt?
No, sir.
Any other doubt till now?
No, sir. Clear, sir.
Clear, no?
Yes, sir.
Okay. Great. So basically, you know what linear combinations are and how we can find it. So let me go to the next one. Now suppose I am giving you 3 vectors, 1, 0, 1, 1, and 2, 5. 3 vector. Yes. Okay. Now I am giving you 5, 3, this point. Can we write 5, 3 as a linear combination of these two? These 3 vectors?
Yes, sir.
Why? Why?
We will simply form a matrix and solve it.
And the equation of this
Sir, first we have to solve and then check, na? We have
2 equations, 3 variables, x,
first
y,
we
and
have
z.
to.
No, sir, I think
Two vectors, 3 vectors will always be.
One by one. So one solution I am getting.
Infinitely many solutions. It will have infinitely many solutions.
It will have infinitely many solutions. That is also okay. Why?
Yes, sir. I am explaining why. Because we have more unknowns than vectors, than R2. I mean, this is R2 space, right? And we have having 3 unknowns. When number of unknowns is more than number of equations, then
number of variables is more than number of equations.
Oh no.
Vice versa.
Yeah, right. So yeah, exactly. So basically, you are writing this. So you have 3 variables and 2 equations you will get, right?
So in this case, we can't make the matrix and determinant, right?
You cannot find the determinant. Yeah, right.
Yes, because it's not a.
But you know how to solve it.
We'll have to solve it.
yes, sir, that's what I was trying to say. That
exactly.
We have more unknowns.
So more variables than number of equations. Correct.
That is why it is having infinitely many solutions. Because one of the variables would be dependent on the other.
Great. So you are writing this. Any other way you can directly say it?
Yes, sir. If we calculate using first 2 points, then we can define 5 by 3 and make this third point 0.
Exactly. Good answer. Yes. So basically, we have already shown that by first 2 points, right? You remember, for this first 2 points, we can express. Okay, let me mute everyone once. Yeah. For the first 2 points, using the first 2 points, we can write it any point on R2 as a linear combination of those two, right? So for 5, 3, I can get something here and here to write it, right? What was the solution for that? 2 and 3, right? Correct?
I didn't get it, sir. How about this? 5 comma 3 is equal to 3, 2.
That was we are doing, no?
Ignore 2 comma 5, no?
This one. C1 is A minus B and C2 was B.
Okay, sir.
Okay, no? And you can check it anyway. If you don't remember that, you can check it. 5 comma 3 I can write as 2 into 1 comma 0 and 3 into 1 comma 1, right? This will give me 5 comma 3. And this solution will be unique, basically. This solution. Now I have one more vector. So if I have one more vector, what I can do? I can put a 0 here. That will solve my problem.
Yeah.
Okay. So basically the large vector which I have added, that is basically redundant. Correct?
So can you please repeat the second method? First one I understood, but the second method that you...
Second method I am saying that I have already shown that this 1 comma 0 and 1 comma 1, these two vector. By using these two vector, I can write any vector of R2 as a linear combination, right? That we have already shown.
Yes, sir.
Do you remember that?
So we don't need a third one, right?
That's what I am telling.
Then we can write every vector using the first two. Then we don't need the third one.
Okay, don't need that, but yeah. So basically this was the combination, right? I can write any vector a comma b as a minus b into 1 comma 0 and b into 1 comma 1.
Yes, sir.
Right, okay. Now, so 5 comma 3 I can write it as 2 into 1 comma 0 and 3 into 1 comma 1. Correct? Now what I have to do with the third vector? I can put a 0 in front of that. Because I don't need that.
So this a comma b is a minus b. This is defined or like is it a formula? Like I'm not getting the link between the two.
This is what we have solved here.
Solved earlier, right?
Solved.
Here. For any a comma b, I am solving C1 and C2. I am getting C2 as b and C1 as a minus b.
So it is. It's already given as a scalar addition. Like an addition predefined, or is it put later on? Like
no, V1 and V2.
Have you joined just now?
Oh yes, sir, I joined a bit late actually.
Basically no. Okay. So it's I want to write a comma b as a linear combination of 1 comma 0 and 1 comma 1. Okay.
Okay.
I want to solve for C1 and C2. If I solve C1 and C2, I will get this as a solution. Okay, is it clear?
Yes, sir. Okay. Yes.
Okay.
Yes.
So my first equation was C1 plus C2 equal to A, and second equation was C2 equal to B. If I solve these two, I will get this solution.
Okay, sir. Yeah,
okay.
I think now
clear, no?
Yes, sir. Yeah.
Okay. You just think a little. I think it will be. This is nothing special. Yeah. So if I have only two vector, which is basically expanding over whole R3, by which I can express any point on R2 as a linear combination of those two vector, then the third one I can make it 0. There is no point in that. Okay. So this is what
I have a question, sir.
Yeah.
If supposing we can't write two vectors as a linear combination of a third vector, so would we say that the third vector doesn't even fall in the same vector space as the first two?
Same vector space means what?
Linear combination. Use the word linear combination. Then your
so if supposing vector v1 and v2 is linear and v3 is not a linear combination of v1 and v2. So can we say v3 does and v1 and v2 fall within the same vector space? So could we say v3
same vector space? What is your vector space?
Linear combination of two vectors.
I'm just giving any example of any vector space because we have not even taken what are v1 and v2. But supposing v1 and v2 fall within a particular vector space,
v1 and v2 is suppose in this case, suppose 1 minute. Suppose in this case 3, 5 and 9, 15. Okay.
Yes.
1, 0 we cannot express as a linear combination of these two. That we have understood, right?
Yes, sir.
Now 3, 5 and 9, 15 is in R2, correct?
Yes.
Third vector is also in R2, right? So that depends which vector space you are talking about.
Maybe
Yes,
the vector
basically,
space defined by
this
that
line,
this line,
exactly.
yeah, on this
Exactly.
line. Then
Yeah.
if in that case, if these two are falling within that vector space, and
Exactly.
because 1, 0 is not a linear combination of that, then we can say
Exactly.
that they're not in the
So
same
that
vector
vector
space.
space, exactly. Good point. Thank you, you bring this up, because this is basically the definition of span of two vectors.
Sorry,
Okay?
this is the definition of
Spanning set.
spanning.
So this is basically span of vectors. Okay, span of some set. So what is span of some set? Span of S. Suppose in S I have some vectors v1 to vk. Okay. So span of S is basically a linear combination of
all vector space.
All such thing. So all the AIs are from R. If I take this will form a vector space. This is a vector space. Okay.
Okay.
So all those vectors which cannot be written as a linear combination of this v1 to vk, right? That will not be inside this vector space, not be inside span of S. Okay.
And therefore will not be in the vector space.
Exactly. So in that case, in our example, I have taken these two vectors, right? This is my v1, this is my v2. Span of S, which we have seen, that is basically the straight line. Yes. This straight line, correct? That was span of S.
All the points which lie on this line are in vector space, and all those points which do not lie on this line, they do not belong
exactly. To and those points which cannot be written as a linear combination, that will not lie inside span of S. So 1, 0 will not lie in span of S. Clear?
Even the element.
Clear.
Excuse me, sir.
So will you be sharing these notes also? This particular ones, please do. Thank you.
Yeah.
So vector space could be a line. It could be a plane, right?
One by one. Naveen, you first ask.
Sir, I am asking. Vector space could be a line. It could be a plane.
Or vector space can be anything. Anything. That depends on in which space are you talking about. In R2, there are only 3 type of vector space. 0, 0, only the point, the whole space R2, and all the line passing through origin, right?
Okay, got it.
In R3, there are more, 0, 0, 0, the origin, the whole R3, then all the line passing through origin, and all the plane passing through origin. There are 4 types.
Okay, sir.
Okay.
R is also vector space, sir.
R is also a vector space.
Sir, so this x is equal to 3 by 5y. So that is that's like an equation, right? That's a formed equation.
So there is a relation between x and y that is given by that. That is a straight line, no? X equal to 3 by 5y.
Yes, sir. So yes, spanning we always have this equation system, right? Like how is it that way?
Span means set of all linear combination of the vectors in a given set. Okay, that is span of S. Right? Now we have already derived that if these two are my vectors in a set, all the points which we can write as a linear combination of these two, that will lie on the straight line. Right? That we have proved. And this one is the straight line. Is it clear?
Okay, so it's in spanning we always have this set which is a straight line, which forms a straight line, right?
Not really. When you are inside R2, that can happen. That may not be a straight line, that can be whole R2 itself.
So could it form a parabola in case of a quadratic?
No, it cannot form a parabola. That's why I am saying it is okay. So as this question is already asked, so I will answer this here now. So inside R2, okay, inside R2 I have a set S, any set. So span of S is a vector space that I have already told. This S is subset of R2. So this vector space, that what this can be. So this is basically a subspace of R2. This part is clear? This part is clear?
Yes, sir.
Oh, yes, sir.
It is bounded.
Now in R2, what can be subspaces? What are the subspaces? First one is only origin, singleton set. Second part is any line passing through origin, that was she was telling. Through origin. And third one is it can be whole R2 itself. It can be whole R2. Okay? So only these three possible cases can happen. So it cannot be any parabola, hyperbola, nothing. Either it has to be line passing through origin, or it can be whole R2 itself. That can also happen.
Sir, whole R2 in the sense like the entire range of real numbers, right?
R cross R.
XY.
R cross R.
XY
Two elements.
1 and 2, the condition 1 and 2 are same now. If 0, 0 satisfied, then the line.
This is not condition. This is just singleton set 0, 0. This is just origin. Just zero vector is in there.
Sir, sir, the third point I did not understand. Like R2.
So if I give you this vector, these two vectors, what is span of S? This is question for everyone. What is span of S?
R2. Entire R square plane.
Right?
Yes, sir.
Is it clear to everyone?
R2, yeah.
Why?
Because we can get
because we can write every term of R2.
Exactly. That I have already shown.
Can be expressed in form of these 2 points.
Any point of R2 can be written as linear combination of 1, 0 and 0, 1. So span of S is basically R2.
Sir, in R2, we cannot, why we are excluding only R? See, R2, only, if it is only R can also be R2.
No, don't mix that up. R is a vector space, separate. Then it is, when I am coming R cross R, this is separate. When I am coming R cross R, that is R3, that is separate. Consider these three as separate, I mean, different vector spaces, distinct vector spaces. Okay.
So can we discuss a span once more, sir, please?
Okay. So span is basically, if I have a set of vectors, suppose V1 to Vk, span is basically set of all linear combination of those vectors. Okay. All those vectors which can be written as a linear combination of the given vectors in that set. Okay. So when I am talking about 3, 5 and 9, 15, I am giving you these two vectors. What is span of these two vectors? We have seen that all these points which is lying on this line,
like this,
right, on this line can be written as linear combination of these two vectors. So our span of S is that line which is passing through origin, x equal to 3 by 5y. Now similarly, if we consider this set 1, 0, 0, 1, what is span of S? Any point of R2 can be written as linear combination of 1, 0 and 0, 1, right?
Yes, sir.
So all these points, all the points of R2 can be written as a linear combination of these two vectors. So span of S is whole R2.
Whole R2.
Now I am saying span of S is always a vector space. Okay. Yeah. Now if my set, the set S which I am taking, that is inside R2, then this is a subspace of R2,
yes,
right?
Yes, sir.
Now what are the possible subspaces of R2? There are three possible subspaces of R2. One is the trivial 0, 0, just only singleton element is there, the zero vector, nothing else.
Yes, sir.
You don't have to bother about that.
Yes, sir.
The rest two are that span of S, I mean the possible subspaces can be any line passing through origin or the whole space R2.
Yeah, whole space R2.
Only these two possible cases are there. So span of S, 0, 0 is basically the set also has to be 0.
Yeah.
Sir, that means the zero vector would always be a subspace of any Rn.
That is the definition of a vector space. 0 should be there.
Yeah.
Sir, then this
after discussing so many questions, if you are asking me whether vector is there, it is.
Sir, I think they are thinking unnecessarily and then they are getting confused.
No. I mean they have missed somewhere.
Yeah. Maybe. Yeah.
So span.
The zero vector has to be there. Okay. It is if it is a subspace, zero vector has to be there.
No, I got that, but I'm saying the single term zero vector can be a subspace of any Rn.
Any Rn 0, I mean, then in
like
R3 it will be 0, 0, 0, right?
Yeah.
Yeah.
The dimension will be different as per the question.
So for any vector subspace, zero vector is a subspace. Okay. For any vector, zero, singleton zero, I mean the zero vector is a subspace. Yeah, that's correct.
Yeah, zero vector is a subspace.
Sir, R2 is the Cartesian plane, right, sir?
R cross R. XY plane.
0, 0 is a subset of R2. Any line passing through origin is a subspace subset of R2.
Subspace of R2, even you can say that. Yeah.
And why are we not considering a line passing cutting x-axis and y-axis? Because it also lies on the Cartesian plane.
0 is not there, no?
But it is on the Cartesian plane, sir.
But 0 is not there.
But what is the
for a
definition
subspace,
of
0 has to be there.
Correct.
For being a subspace, 0 has to be there. 0 vector has to be there. Is 0 vector is in this line?
No.
I understand, sir. 0 vector has to be there. I want to know the reason, please. I guess I have forgotten.
That is the
For definition of subspace, 0 vector has to be there.
Constant.
You can say this 1 minute. You can say this line is a subset, but not a subspace.
Okay.
I am saying talking about subspace.
For a line to be a subspace, 0 vector has to be there.
Exactly.
It is valid for Rn as well.
Any
dimension.
And sir, last question, sir. What is the meaning of subspace of R2 being R2? The third
whole
point.
space becomes a subspace.
The same question. I'm also confused little bit.
Yes, sir. I guess Pratika was also asking the same question.
In maths 1, okay, I am answering that. In maths 1, have you said that A is a subset of itself? Any set is a subset of itself?
Yes, sir.
Yes, sir.
Same thing. A vector space is a subset of itself.
So the question is, sir. Okay, sir, got it. So R2 subspace R2, what we are saying is the Cartesian plane with origin.
Sir, basically what is given in the question, that itself is R2, right? 1, 0 and 0, 1 is R2 in this case, right?
R2 is the whole plane. 1, 0 and 0, 1 is just two vector in there.
Sir, and okay, but then the whole set of
You tell me what is R2 first. Now I am really...
all the points.
What is R2?
All the points. Any set of 2 points which are real numbers.
Any set of 2 points?
Sir, like 2 points in a vector. I mean, like a tuple of 2 points.
Any tuple, right?
Exactly.
So 1, 5, 7, 39, all these points, right?
Yes, sir. Yeah.
So all the points are, I mean, the set of all these points are R2, right? Yes. Now these 2 points are just 2 points in R2, right? 2 different points in R2.
Yes.
My point is only these 2 points can span whole R2. Means take any point from R2, A comma B, that can be written as a linear combination by these 2 vectors. Okay, that's why span of S is whole R2. Is it clear?
Yes, sir, got it, sir.
Sir, and subspace, like what is the significance of a subspace? Like why are we studying that? Like in
that I will come later. First tell me, have you understood why R2 is a subspace of itself?
Yes, sir.
Why?
I'm not able to explain, but
can I explain?
Yeah, someone else can please. Yeah.
Go ahead.
Because
any set
we can please let me. Because we can choose any random point in the Cartesian plane and we can connect it via origin.
What is that?
Because we can choose any coordinate point x comma y, and that coordinate point will of course can be connected via origin from 0, 0 to that point. So that is the definition of subspace now.
No, when I have said that is the definition of subspace. I mean, that is the definition of what? Nothing.
So
Excuse me, sir?
Geometric representation, sir.
No, not really.
Sir,
You're saying you take any point and connect it to the origin, then?
So it is a subspace of R2. That point.
Point is not a subspace. Subspace, I mean, how a point can be a subspace other than origin?
Tuple can be.
Point cannot be a subspace. No, subspace means a set. First of all, a set has to be there.
Sir, can I Can I express?
So many, all of the points lying on that line, connecting that 2 points, 0, 0, and that point.
So how you are getting whole R2?
Because we can select infinite.
So suppose I am drawing this line. This is a point, okay, on this line.
Yes, sir.
I am connecting with 0, 0. Is this line a subspace?
No, sir. No, not that line is a
subspace. According to your definition, it is.
Actually,
no, sir. No, sir. I did not mean that, sir.
Space.
So what do you mean? I mean, clarify that first.
I'm not,
when one person is talking, can you please hold your question? Then it will be great. Okay.
I was not drawing. I was not drawing any lines, sir. I was just choosing a point and
you are saying connecting with 0, 0, no?
If it is connected, if we can connect it via 0, 0.
That's what I am doing, no? You have to give me a set first, okay? No. What is your set? For subspace, what is your set?
Sir,
X comma Y.
Sir, actually,
Any X comma Y in
the
R2.
scaling of.
If we scale, then we will get with 1, 0 and 0, 1.
That point only he told.
A comma B.
May I share my review?
Sir, subset is a subspace is a subset of a space.
First of all, it has to be a subset, right? So my point is, suppose I am giving you this straight line. Is it a subspace?
Yes.
Yes, sir.
Why?
Because it's a subset of R2.
Define your actual set.
Because it is 1 minute.
Because it is a subset of R2.
So any subset of R2 you are saying as a subspace?
No, sir. It has to pass from origin. That set of tuples.
Right.
0, 0,
okay.
0.
Right.
That is what I
basically.
On all of this.
Okay. So basically, let me recall
sir,
once.
how can you say that it is entire R2? That's basically only that points which passes through the origin, right? I mean,
those set.
Exactly. Those set of tuples which pass through the origin and is included, that is itself is included in R2. How can it be entire
First
R2?
of all, you have to remember what is the definition of subspace. Okay. Suppose I have a vector space V. Okay.
Yes,
W is a subspace if W is a subset of V which satisfy these 3 conditions. 0 should be inside W.
Yes.
If I take two vector from W, the addition should be inside W. And if I take any vector from W and any real number, this should be
scalar multiples.
W. Right? This definition is clear?
Yes, sir.
Yes.
Okay. Okay. Now come. Suppose V is R2. Okay. I am taking my W to be R2. Can I take that? Is R2 is a subset of R2? This first property, this one.
Yes,
is this satisfied?
Yes, sir.
Is this satisfied, everyone?
Yes.
R2 is a subset of R2. That is clear? Okay.
Yes, sir. V is R2 and W
origin
is R2.
Is there? Yes. Origin is there?
Yes, sir.
Okay.
Yes, sir.
If I add 2 points from R2, will it be a point in R2?
Yes, sir.
So that means
if I take
subset of
yes,
R2.
1 minute. If I take any point in R2 and do scalar multiplication with that, the result we get, that is also in R2?
Yes, sir.
So scalar multiplication part I get, but addition part, we'll have to check whether it passes through origin or not.
Why? No, addition part does not say that. Addition part is saying you add 2 vectors from there, it should be lie inside there. You take 2 points from R2.
Just it has to lie with, in W.
In R2. Yeah. Because all are the different.
You take any 2 points, A comma B and C comma D. Your addition is this. Is not this point in R2?
Yes, sir, because A plus C is the real number and B plus D is the
then
real
why you are taking this, passing through origin business?
All lines will not pass through the origin.
You may watch the
fly in the
plane. We were discussing the beginning.
Okay, 1 minute. So first of all, tell me, R2 is a subspace, is it clear or not?
Yes, sir.
Yes, sir.
Clear, sir.
Anybody has any doubt at this point?
No, sir.
W is a subset of R2 then.
Shall I speak, sir?
Yeah, go ahead.
Sir, they are forgetting the spanning set, sir. Means,
no, I am not mentioning our spanning set now. I am not spanning out. My question is, I mean, this is very basic. I have vector space R2, and can I call R2 as a subspace of itself? That
Yes,
is the
sir.
basic question.
Yes, yes.
I was trying to explain
Yes, we can
where
call
they
it.
are going wrong, sir.
Yes,
Yes.
yes,
Going by the definition, we can call it, sir.
Subset of.
Anybody has any doubt till this point can ask me. Because this had to be clear anyway. My point is any vector, take any vector space. It is a subspace of itself.
Sir, definition
Sir,
wise,
how
it is
R2
clear,
a
sir.
subset of R2?
Then by which wise it is not clear?
Sir, geometrically, pardon, sir, please. I'm
Geometrically
sorry.
it is not clear. If you have a vector space, is it not a subspace of itself? Subspace means what? It has to be vector space and it has to be subspace. Subset.
So
Is not V is a subset of itself?
Yes, sir, got it, sir.
Right?
Yes, sir.
And geometrically also, what is the issue? If, I mean, this is your Cartesian plane. This is a vector space, no?
Yes, sir. Any point within this Cartesian plane will be subset of itself. Yes, sir.
Subset of, no, any point is not a set of all points. What is your R2? R2 is all, whole thing, everything.
Yes, sir.
Not
Set
a
of,
single point.
Yes, sir. Set of two tuples.
Yes, including 0, 0.
Including
zero.
everything. Okay. So
Okay,
basically,
sir,
so there is nothing much. I mean, I don't know why I am doing this at all.
Sir, can I say the last line, sir?
Yeah, go ahead.
Tuples, all tuples including 0, 0 will form the subspace, right, sir? Including 0, 0.
That
all
is
tuples. That is.
I mean, why are you saying this? I am not really getting an idea. Basically,
the confusion
my point
of 0,
is.
0. The confusion
My point
of 0
is 1 minute. My point is, if I have vector space V, okay, V is a subset of itself, right?
Yes, sir.
Which is a vector space.
Yes.
So it is a subspace.
Okay, sir, got it.
Any set is a subset of itself. Is that part clear from Maths 1?
Yes, sir. Yes, sir. Yes, sir.
The same thing is happening here. V is a subset of itself. That is enough. You don't have to check anything because we already know V is a vector space.
Okay, sir.
So R2 is a subset of R2 itself and R2 is a vector space. Right?
Yes, sir. Yes, sir.
You don't have any doubt about R2 is a vector space, right?
No, sir.
At that point, you don't have a doubt, right?
No, sir. No, sir.
And R2 is a subset of itself. That point is also clear, right?
Yes, sir. Yes, sir.
And that is the definition of subspace.
Can I say something that resolves this?
1 minute. So this part is clear?
Yes, sir. Yes, sir.
Now, what are other subspaces of R2?
0, 0.
There must be
only point 0, 0, the 0 vector. Yeah, right. And
addition of 2 vector must be there.
Yes, sir. Any 2
that
points.
is okay. That is okay. What are other type of subspaces are there in R2?
Any line passing through the origin.
Any line passing through origin. Exactly.
And the
because only those lines will contain 0, 0.
Yes, 0.
Yes, sir. Yes, sir.
Clear?
Yes, sir. By
is
saying
this
that,
clear to everybody?
Sir,
Yes,
by saying a line, we mean that all the tuples
on the line,
on that line, including 0, 0, of course.
That is the definition of line. Yeah.
Yes, sir. Yes, I got it.
Got it? No? Clear, no?
Yes, sir. Yes, sir. Crystal clear.
Anybody has any doubt at this point?
No, sir.
Okay,
No, sir.
Okay. I mean, there was one more girl who was confused in this. I forgot her name.
I think
Pratika, I guess.
I got it, sir. I mean, after such
Pratika,
elaborate
right.
explanation, I think it's very clear. Thank you, sir.
Now it is clear, right?
Yes, sir.
Because this is very basic. If you have a doubt here, then it will be very difficult in later week. That's why I am spending so much time in these places. Clear, no? It's clear?
Yes, sir. Yes, sir. Yes, sir.
Okay, yes, great. Now, from this discussion, can you tell me what are subspaces of R3?
Yes, sir. May I share my view?
Yeah, sure. Go ahead.
Sir, for R3, there are 3 kinds of subspaces. One, a point 0, 0. Second, any ray in any direction which cross the point 0, 0, 0.
Any line.
Any line passing through origin.
Yes.
passing
third
through the
is
origin.
Any plane passing through origin.
Sir, I think we can take
sir.
any plane
Sir,
passing through origin as well.
And then
And then the R3 itself.
R3
R3
itself.
Great. So I hope you
And
understand.
fourth is any volume, any 3D.
Not any volume.
R3 itself.
Any
R3
state.
itself. Yeah.
Clear? So these four are subspaces of R3. I hope it is clear to everyone, right? You can
Yes,
visualize this also, right?
Yes, yes.
The same geometrical thing we are doing. Okay, good. So span we discussed more or less. So one thing it is remaining, that is linear dependence and independence.
And dependent and independent.
Span, sir, span.
Span we have discussed.
That has already been discussed.
And I will again come to span. I mean, the basic definition is clear, right? A set of all linear combination of the vectors. Right?
Yes, sir. Yes, sir.
Move to
Yes, sir.
dependent and
always remember span is a subspace.
That is A comma B, sir. Span. That we were finding earlier.
No.
The set of all such A comma B's, right, sir?
No. Span means set of all linear combination of the given vectors in a set. Okay. What I said is, if that depends on the vectors given. So if I give these two vectors 1, 0, 0, 1, then any point of R2 can be written as a linear combination and like this, A, B is this, right?
Yes, sir.
So span of S is the whole space, but it cannot be the whole space also. This example also I have given. If I take 3, 5 and 9, 15 as my points, then span of S is basically the line x equal to 3 by 5y, right? These two we have seen. Clear?
Sir, let us discuss this dependence and independence.
So I will go to that now. So linear dependence and independence. Okay. So suppose I have some vector vk, okay, and I am writing 0 as the linear combination of these points. I am writing the 0 vector of the vector space. Okay. So what I am doing? So let's try with concrete point. So suppose I am taking two vectors. I want to write 0 as a linear combination of it. So this is x, this is y. I want to find it, and this is 0, 0. As I am doing it in R2. So what are these two vectors? What are the solution for these two vectors?
X plus y is equal to 0 and x plus 5y is equal to 0. So it is minus 4y is equal to 0. That is y is equal to 0.
So basically there is only one solution.
X comma is equal to y is equal to 0.
Unique solution. Right?
Yes.
Unique solution.
Correct.
So this x and y have unique solution and both are 0. If this type of situation happen, means all these ai's are 0. All ai's for all I.
All
then
coefficients.
Then this set, this v1 to vk, this is called linearly independent. Okay. Why we call this, I will come later, but first try to understand the definition. Now, if some situation can happen, 1, 1 plus 3, 3, can there be any solution for x and y in this case?
It can be
Sir,
0,
any
0.
solution means other than
0, 0 is the solution. Yes, you are
It will have
right.
infinitely many solutions, I guess.
Can you give me one?
Yes,
C1
minus 1 upon 3 on the onto the second one.
Can I write this?
Yeah.
C minus
Write this as well. Yes.
Minus
So
anything,
3,
anything that yields 0.
yes, all the multiple.
Exactly. So there is a non-zero solution, right?
Correct.
There are infinitely many solutions, as you have said, but there is a non-zero solution. So from this infinite thing, we can choose any one of these. So there is a non-zero solution. So if this type of situation happen, then we call, that means if one of these ai's are non-zero, at least one of these, okay?
Yes.
Then we say that, so if at least one of the ai's are non-zero, then we call it linearly dependent. Okay.
Yes.
Now, in these two examples, what you are observing, if you plot this, where is 1, 1? Somewhere here. 1, 5, somewhere here. Right?
Yes, sir.
As I was showing earlier,
They're not in the
they are not collinear. They are not on the same subspace. Right? They are on different subspaces.
Having a unique solution 0, 0.
Exactly. If you draw this, both of them will line on same subspace.
Same subspace.
Same straight line, same subspace. So basically,
X is
here
equal to
what
Y.
you are doing, you can write this 3, 3 as a scalar multiple of 1, 1. So they will line on same subspace.
Yes,
right?
sir.
That's why they are linearly dependent. And that's why here they are not linearly dependent. That means linearly independent.
Yes, sir.
Okay? Is it clear?
Yes, sir.
Okay. Good. For R2 it is clear. Now, suppose I have 3 vectors. 1, 0, 1, 1 and 2, 5. I have taken this example a lot of time earlier also. So I have these 3 vectors. Okay. Now, my question is, suppose this is S. Is S linearly independent? This question. This is my question. So what I can do? The same thing I can do, right?
Yes, sir. Yes, sir.
I want to solve this system. I want to write 0, 0 as a linear combination and check whether x, y, z can have a solution or not, non-zero solution or not.
Yes,
right?
sir. Yes, sir.
So x plus y plus 2z and y plus 5z, 0, 0. So by just
Sir,
seeing
or
this,
like writing
The number of unknowns, again, number of unknowns is greater than number of equations.
so there are infinite solutions that you know,
So
right?
there are infinite
Yes, sir.
solutions.
Let him
So there must be a non-zero solution, correct?
Yeah. Yes, sir.
So this is linearly dependent, correct?
Correct.
Okay. Yes. I guess
Sir,
someone has any other
like
yeah.
just writing 0, 0 on the right hand side, like taking a 0 vector on the right hand side, always does it mean we get whether it's dependent or independent?
That is the definition
way?
of dependency and independency. Yeah.
Acha. Sir,
So
but like,
if
what's
you
the
can
logic
write,
in that? Like,
basically that's what I am trying to say. That this the spanning set by these vectors, are they somehow related or not? And now spanning set means what? They are subspaces, right? So say they must contain 0, 0. Right? So basically you are seeing whether all these subspaces generated by those, are they related or not? Are they lying in the same subspace or not?
Yes, sir.
Are they dependent on each other or not?
So basically what you are doing, so in this three set, set of 3 elements. So you know 1, 0, 1, 0 means the subspace generated by this is basically the x axis, right?
X axis, yes, sir.
And the subspaces generated by 1, 1 is basically
straight line x is equal to
line
y.
x equal to y line, correct?
Yes.
So
sir.
these 2 subspaces. Now the third one, your question is 2, 5 is inside span of 1, 0 and 1, 1 or not? The subspace is generated by these 2. That is your question. Is it clear? If this is inside the span of this, then it is linearly independent. If it is not, then it is linearly independent.
So are we supposed to make a vector
sir, it is
addition of
inside
1, 0 and 1, 1, or just to check whether 2, 5 lies on these 2 lines or not? Or we have to add them linearly?
2, 5 does not line in these 2 lines, but that does not mean it is linearly independent.
So we have to
that's
add,
what I'm
add up.
not getting. That why is it so? Like, it's not a multiple. Then how is it that it's linearly dependent?
So this is the question. This is the question.
Are we supposed to add, make sure that the addition of these 2 vectors 1, 0 and 1, 1, whether after adding these 2, whether 2.5 lies on 2.5 lies on that added vector or not?
2.5 not added vector lies in the span of these 2 vectors.
Yes, sir. Yes, a span of
Yes.
those 2
I
vectors.
think
So,
yes.
yeah, that is the question.
It lies on this.
Yeah,
That
exactly.
will lie. That
So,
will lie. Yeah.
So basically, first what you have to check. Suppose you are first, so start with a singleton vector 1, 0. Any singleton vector is always linearly independent. Can you tell me why? I am coming to this question later. Any singleton non-zero vector is linearly independent. Can you tell me why?
Can multiply it with 0.
So if I write C into V equal to 0, then only solution for C is basically 0 if V is non-zero.
Yes, sir.
Right?
Yes, sir. V is a non-zero.
This is clear, right?
Yeah.
No issues there. So this is linearly independent. That we know. This is linearly independent.
Absurd.
Which is absurd?
C V1 equals 0.
That only solution is C is 0. Right?
Sir, I'm not getting this point, sir.
C into V is 0. The only solution is C is 0.
Yes, sir.
Right?
Because
V
is not
clear,
0.
no?
Yes.
For
We
non-zero
can't
vector,
be
right?
0. We can't be 0, no? Yeah.
So
I am saying non-zero vector.
So every singleton vector is independent, linearly independent.
Exactly. Every singleton vector, singleton set of non-zero vector is linearly independent.
Non-zero vector, right? Yeah.
Yeah. Non-zero vector is linearly independent. Now I am adding one more vector to this. 1, 1. If I have two vector, now what is the point? I have to check if one vector is scalar multiple of other. Right?
Sir, one thing I want to ask, yes, please. I want to pause you for a moment. This is a vector in R2, and every singleton vector is linearly independent. So, what if the vector is in R3? Is it then also linearly independent?
For any vector space. So that's why I am calling C into V0 for any V. I am not mentioning in R2, R3 anything. It can be any vector in any vector space. The only solution is C.
If it is singleton, then it is linearly independent.
Exactly. Okay.
Can
Now I have another vector.
Like you just previously showed it. Can you please geometrically show it?
Which one?
Because the singleton vector unique solution part, sir.
I am not getting what you want to see.
So I want to see the geometrical representation of the fact that all the singleton vectors are linearly independent.
So if you take any vector in, suppose in R2 I am taking. Now
it will pass from origin. That's why it is.
I mean, there is no other vector for dependency, right?
Okay.
I mean, what
it is not dependent. It is not dependent on any other vector.
Right.
It is.
Clear?
Yes, sir. Got it. Sir.
The dependency comes when the second vector is coming. Like in this case.
Then we have to linearly add them and then check for dependency. Yes.
Yeah, right. So when the second vector is coming.
Can I interrupt on this point?
That
part is clear because there is only one vector, it is independent. But why is 0, 0 dependent?
Why is 0, 0 dependent? Good point. So 0, 0 means what? So
coefficient can be 1.
Coefficient, if you take any coefficient here.
Coefficient could be anything. Coefficient could be anything.
So I can write it, right? I can express 0, 0 as a linear combination of 0, 0.
Of anything. We can represent the 0, 0 as a linear combination of any vector.
Thank you.
Yeah.
Thank you.
Correct.
Works.
Yeah, no?
Yes.
Okay.
So sir, it is dependent.
0, 0 is linearly dependent. This one. Okay.
Hello, sir.
Why so? What is the reason?
Just now I have said, no?
Yes.
You can write 0, 0 as. So you can take any real number, any non-zero real number here. And that was the definition earlier I was mentioning, no?
Hello, sir.
All the AI should be 0 for linearly independent. But 1 minute, when I am explaining something, can you please hold your question? Yeah.
Okay.
So when I am saying 0, 0, this coefficient, what I can take here, I can take any coefficient, let's say 1. So this gives me a linear combination, right? With non-zero coefficient to express 0, 0. Is it clear?
Yes.
Is it clear?
Yes, sir. Clear.
Yes, sir.
No, who is asking the question, she has to tell me.
Yes, sir. Clear, sir. Yes.
Okay.
Sir,
yeah.
Sir, what will happen? What will happen? Suppose we take 0 into 1 1 plus 0 into 0 0. Is it independent vector? Is it
Which
independent?
one? What is your vector? What are your vectors?
0, 0, 0,
3,
0.
0.
Yeah, sir. 0 into 0, 0 means
No,
0.
don't take the coefficient. First, tell me what are your vectors.
Vectors is like I think this is activity question 3.4.
That's why I was asking what are your vectors. Don't
Yes,
ask me
so,
for solution.
I don't know, sir, but question is
You have
asking
given some vector, right?
Vector.
What are your vectors?
Vector.
You know what is a vector, right?
Yeah, suppose x is equal vector is like.
Were you present in my live session from the beginning, or you have joined just now? Hello? You have joined just now,
Just
or you
now,
are
sir.
present?
I have joined
just now, no? So can I request you one thing? You go ahead and see my earlier live session and this live session also.
Yeah.
Okay, then I think it will be helpful. Otherwise, I mean, from in between it is difficult, no?
Yes, sir. We are repeating same point again and again.
Okay, you just go ahead and see the live session, and then if you have doubt, you can ask me later. Okay.
Okay.
Okay. So where are we? So if I add one more vector to this set, suppose 1, 1, what will happen now?
Sir, it
So,
is linear.
So basically, we have to check by the subspace generated by 1, 0, is 1, 1 lie on that set. Basically, is 1, 1 is in span of this 1, 0. Right? That's what we are checking. Right? Now, span of 1, 0 means what? Can someone answer that? What is span of 1, 0?
All that can be written as a combination of 1, 0.
So basically C into 1, 0, right?
Yeah.
All these points. So what are these points?
X-axis. Complete
X-axis. Great. It is completely X-axis, right?
Yes.
C, 0 points. So all the points which lie on the X-axis. Right? Now is 1, 1 lie on X-axis?
No, sir.
So this set is also linearly independent. Till this point it is clear?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So this will explain why we are basically trying to express everything as a linear combination of 0, 0.
The last point, sir. You just said that 1, 1 is linearly independent, or 1, 0, 1.1, 1, 1 is linearly independent.
This whole set is linearly independent.
Yes, sir. Got it. From each other, with each other.
They are linearly from each other. Yeah. But here we basically talk about a set is linearly independent or not. Okay.
Yes, sir.
Okay. Now I will add one more point.
Sir, if I may ask a question. You have explained linear independence and dependence through the coefficients, whether they're non-zero and 0. But graphically also you had explained, I didn't get it clearly. Can I ask for small clarification? So if we have two lines, both passing from the origin, but which are not overlapping, then if two vectors lie on these two separate lines, then we would say they're linearly independent?
What? Sorry, I missed. Again, can you
I'm
tell
so
me?
sorry.
Repeat again?
If I take two vectors and I join those particular coordinates with the origin so that they lie on two separate lines
like
passing
this
through
one,
the origin,
right?
both passing through the origin, then would we
both are
say
passing
that
through
they're
origin.
linearly independent just graphically?
No, I mean, we don't need that one. That's what I was telling right now. So see, again, I am going back there. Okay. So 1, 0 is linearly independent. That part is clear, right?
Yes, sir.
Okay. Then I am adding another vector 1, 1, and I am saying whether 1, 1 lies in the spanning set of 1, 0 or not. Right?
Yes.
That was my question. Now, what is spanning set of 1, 0? 1, 0, that is x-axis, right? The line passing through this.
Right. Yes.
Correct?
Only there
now,
would they be
is
multiple.
1, 1. Exactly. Now, is 1, 1 lying in this set?
No.
No. So 1, 1 lie here. So we can say these two are linearly independent, right?
Yeah, but
Okay?
this is
The same
for
thing.
one lying on x-axis and the other on. But even
Now
if they
I
were
am
not lying.
now I'm coming to that. Okay. Okay. Now I am adding another vector. Okay. 2, 5.
Yes, sir.
Okay. Now my question is 2, 5 in span of these two vectors? This set. Now what I have to do?
Yeah.
So this is 1, 0. This line is basically spanning set of 1, 1.
Right.
Okay.
Yes.
But 2, 5 does not lie in any one of those.
Yes.
Right? But that does not guarantee that 2, 5 is not in span. Right? Because span means what? All the linear combination of these 2 points. So this first x-axis is only the linear combination of 1, 0. This line x equal to y is only the linear combination of 1, 1. But we have not yet considered the linear combination of both. Right?
Okay.
Yes, sir. Yes, sir.
So we cannot say still. Okay. So what we have to do? We have to find out what is span of 1, 0 and 1, 1. That means span of this.
So there is no alternative other than that solving for that.
Yeah, right.
Of course.
So
we
basically,
can't do it
there are some techniques which I will express, but first make this fundamental clear. Okay.
Yes.
Then find for trick. You can find it yourself. So my question was this: whether 2, 5 can be written as this, right?
Yes, sir.
Now you already know the answer.
Yes,
right?
because we did a minus b into 1, 0 plus b.
Because any point of R2 can be written as linear combination of 1, 0 and 1, 1.
Yes.
That we have seen. Because
one thing,
span of
number of
1 minute.
Okay, yeah, we saw the span of 1, 0 and 1, 1 is actually R2. Yeah.
This was R2. So any point on R2 can be written. So
accordingly, 2,
this
5
answer
would
is yes.
definitely be in span of that.
So this is linearly dependent.
Yeah, got it, sir. Thank you.
Is this clear to everyone?
Yes, sir.
Yeah,
now you can ask question. Yeah.
Yeah. These three points. Hello.
One by one. One person is talking. Then why others are talking? Yeah. Go ahead.
Yes, 3.4 activity question 3.4.
Activity I am not solving.
Yes, sir. Can I take question?
If you have any conceptual doubt regarding that, then I can answer.
Can I take question?
Can you do that?
Hello, sir. Are we going to discuss any new topics, sir? Because we have got Python session as well.
Sir,
you can leave.
Like this span concept, sir, how you have taken that 2, 5 lies in R2.
Why 2, 5 lies in R2?
No, sir. How you have checked that these are this is linearly dependent 2, 5.
This whole set is linearly dependent because 2, 5 lies in the span of 1, 0 and 1, 1.
So how can you guarantee that?
Because span of 1, 0 and 1, 1 is whole R2. That we have already seen, no? Any point in R2 can be written as a linear combination of 1, 0 and 1, 1. So I can really find A and B for this.
Yes.
Right?
Okay, we don't need the third one, right? You mean to say that we don't need the third one? So
no, if I add third one, then it will be linearly dependent.
Yes, sir.
Sir, can you give one example of 3 tuples where it is linearly independent?
I am coming to that, but first make it clear. So tell me the solution for the A and B here. Yeah, Pritika, I think. Yeah, you tell me the solution of A and B.
Sir, I think it's 1 plus 1 plus 1.
B is equal to 5.
Is it?
Yeah, no, 5.
Is equal to
Sorry,
minus
1 plus 5, is it 2, 5?
No,
5
sir.
or minus 2, sir.
So I think minus
2.
Yeah, minus 4.
minus
Okay. Yeah.
Minus 3.
Minus 3.
Minus 3 you can write.
Minus 3. Yeah. So what I get here, now if you coming to the Pritika's question which I have started with. So I have minus 3, 1, 0 plus 5, 1, 1 equal to 2, 5. So basically this shows that 2, 5 is in span of 1, 0 and 1, 1, right? This part is clear to everyone?
Yes.
Yes.
Right?
Yes, sir.
Now what I can do, I can take 2, 5 this side. So this is 0, 0, correct?
Yes.
Correct?
Yes.
So this is minus 3. So I can write is plus of minus 1. So basically, see what I have made. I am getting some non-zero coefficient to make the combination 0, 0. Right? That was the definition I have started with. This. Is it clear now, everyone?
Yes, sir.
Yes, sir.
Yeah, this method is clear, but sometimes I solve by deducing with a unit vector. Like if I deduct 1, 1 from 1, 0, I will get 0, 1. So this will become a unit vector of x and y axis. So
that will be difficult in some cases, no?
So I used to solve like this because with the background.
Try to make it little more easier for you by using this concept. That will be better.
Sir, one question. Can you just stop here? Sir, here we have 1, 1 and 0, 1. So 1, 1 is 45 degree slope and 0, 1 is 0 degree. So anything 2, 5, it is between 0 and 45 degrees. So can we conclude that it is?
There is nothing related with degree and all these things.
No. I'm just telling you because this is.
Nothing related to that. No.
Nothing. It has nothing to do.
Nothing to do with degree and anything.
Area
nothing to do with that.
Not take a space has to be area on a coordinate plane because a line is also a vector space.
I mean, any point, if you take any point here also, that is also in span of these two, 1, 1 and 1, 0, right? Here, anywhere, any point in up to.
Okay.
Okay, no? Have you understood this statement? Span of 1, 0 and 1, 1 is up to?
Yes, sir.
Yes, sir. Yes.
No, so, I mean, Krishna ji was asking this question, right?
Yes, sir.
So you have understood this, no?
Yes.
So basically, any point in up to can be expressed as a linear combination of these two. Okay. So does not matter where the point lies. Okay?
If a set of vectors are given and it is not something which is basic, like what we are having here, 1, 0 and 1, 1.
You have to solve the system of linear equation, no other way.
Okay.
So if the set
now I am telling you some tricks here. Okay.
Yes.
So for R2, okay, if a set contains more than 2 vectors, set contains more than 2 vectors, then it is. You can tell me it is.
Dependent.
Right? Clear? Is it clear?
Yes.
Yeah. Because what can happen? It can happen that suppose V1, V2, V3, 3 vectors are there. Okay. It can happen that all these V1 and V3, V2 and V3, both are multiple of V1. That can happen, right? That is the first case. Trivial case that can happen, then anyway you don't have to find anything because V2 itself is in span of V1. That can happen. So if that does not happen, then what is the possibility? That V1 and V2 are independent, right? This V1 and V2, like in this case I have considered this case, that V1 and V2 are not linearly dependent. They are independent to each other, right? If I only consider V1 and V2 set, it is independent of each other. Now, in this case, it always happens that span of this is whole R2 if they are linearly independent. Why that is true, I will tell you in week 4. Okay, I will not go into the details of this, but if V1 and V2, I am writing this, if V1 and V2, I mean this set, if V1, V2 is linearly independent, then span of V1 and V2 is R2. Okay. Now, if span of V1 and V2 is R2, then V3 must be inside that, in the span, then it must be linearly dependent. Clear? So, if in R2 you have a set which contains 3 or more vectors, that means more than 2 vectors, then it must be linearly dependent. Clear? Clear?
Yes.
If
Yes, sir.
okay, in R3, if a set content more than 3 vectors, then it is linearly dependent. Same logic. Okay. By same logic, if in R3 a set contain more than 3 vectors, then it is linearly dependent. Now the problem arises. Now, what are the other cases? So most of the cases you have to deal with R2 and R3 only. Okay. That's why I am talking about these two. Now in R2, you are given only 2 vectors. More than 2 you know linearly dependent. For 2 vector you have to check, right?
Yes. Yes. Yes.
Right. So 2 vector means what? One vector will be like suppose 5, 7, and another vector like 1, minus 3. Right? Like this, 2 vector. First way to check is one is multiple of other. If that happens, then it is linearly dependent. If one, if suppose V2 is scalar multiple of V1, then linearly dependent. Scalar multiple means not only integers. You remember scalar means any real number, right? Okay. What are the other way to check? Which is better way to check? Write these as column. Find the determinant. If determinant, write it this. So if determinant of A is non-zero, then linearly independent. If 0, then linearly dependent. Can you tell me why? I have already explained it. Why this method is working? Determinant thing.
Because
it is invertible.
Exactly, because you have to write the coefficient, right?
Yeah.
You have to try to find the coefficient. What is the solution for the coefficient? So what you are doing basically, you are trying to find this solution, right?
Sir?
1 minute. Let me explain this, then you can ask. So you are getting these two equation, right? So homogeneous equation 5, 1, 7, minus 3. C1, C2 is 0. Now, you know homogeneous system of equation, it has a unique solution if it has, I mean, this is invertible. If it is not, then there is infinitely many solution. There are infinitely many solution. That means there is non-zero solution, correct? So only unique solution means the solution must be 0, 0, correct? For Ax equal to 0, if it has unique solution, then X must be 0, right? Is it clear to everyone? I mean, this is quite trivial, right? If X equal to 0 has a unique solution, then it must be 0 because 0 is already a solution.
Yes, sir. Yes, sir.
Yes, sir.
Correct? There cannot be any other solution. 0 is the only solution if it is unique, right? And if it has infinite, otherwise it has infinitely many solution. Let me write that. I mean, no solution case is not possible here because 0 is always a solution. Okay? Otherwise, it has infinitely many solution. Only 2 cases are possible. Now, for this, you need A to be invertible. And for this, A not invertible. Now, when A is invertible, determinant A is non-zero. Determinant A is 0, right? So when unique solution is 0, that means it is linearly independent. All the coefficients are 0. Infinitely many solution means there is non-zero solution. So there are non-zero solutions. That means it is linearly dependent. Is it clear to everyone what I have written?
Yes, sir.
Yes, sir.
Very clear?
Yes,
Sir,
sir.
can I check R3 in the same way?
Exactly. I am coming to that. Okay. So this part is clear, right? So in this case, you can see determinant is minus 15, minus 7, minus 22, so non-zero basically.
Sir, here
So this is
determinant A not equal to 0, linearly independent, equal to
exactly
0, linearly dependent.
I have written it wrong. Correct.
So, sir,
independent. Yeah.
Sir, can we say that on that concept, vector 0, 0 and vector 1, 1 is linearly dependent?
I will come to your question one minute later. Okay. I will come to that. So in R3 also, if you have three vector, why you need three vector? Because otherwise it will not form a square matrix. You cannot calculate the determinant, right?
Yes.
So more than three case is solved. It is, if it's more than three, it is linearly dependent. If you have three vector, you check this determinant thing. If determinant A is 0, it is linearly dependent. Same logic you can see. And determinant non-zero means linearly independent. Okay. What happens if there are two vector? You can check directly from writing the equations or check whether one is scalar multiple of another. Whether V2 is scalar multiple of other. Scalar multiple of V1. Okay. If that happens, it is linearly dependent. Correct? So this basically exhausts all our cases except the question he has asked. So if you see a zero vector in a set, the set must be linearly dependent. Why?
Because
why?
Because we can write it as a linear combination of any.
It will make everything zero. Because
Exactly.
Zero.
Exactly. So if you have 0, V1,
Sir,
V2.
Please give example of the next point. V2 is scalar multiple of.
I am giving that. So first, if one vector is 0, so you can take 1 into 0 and rest you can take 0, 0. No issue. This will give you 0 vector, right? So at least one non-zero coefficient is there. So this set is linearly dependent. Correct? Clear to everyone?
Yes.
Okay. Now this scalar multiple thing in R3, say suppose two vector 1, 3, minus 7 and say anything minus 7, minus 21, sorry, and what should be 49. Is this set linearly dependent or independent?
Independent.
Independent.
Dependent.
Sorry, dependent. It is a scalar. Okay.
Infinitely many solutions.
Because one is scalar multiple of the other.
Yes.
So it is dependent.
It is dependent. Because then you can take it on the same side and you will get a non-zero solution. Clear?
Minus 7 and minus 1 non-zero solution.
Yes.
These are non-zero. Yes, you can check it directly by writing equation. That is also okay, but that will take time. Okay. So this is basically the gist which we are trying to discuss today. So everything, as I have telling from the beginning, it is related to linear system of linear equation. When I am coming to linear dependence and independence, it is basically solution of system of linear equation of homogeneous equation basically. Ax equal to 0. Now Ax equal to 0 can have only two type of solution, either one unique solution or infinitely many solution. No solution case cannot happen there because 0 is already a solution. Right? Now unique solution means the solution is exactly 0. That means all the coefficients are 0. That means it is linearly independent. So basically we have to check the determinant is 0 or non-zero. If determinant is non-zero, then it is linearly independent. If determinant is 0, it is linearly dependent. Now, the other cases I have already discussed. I think if you just go through this PDF once, you will get everything of this chapter.
Sir, can I
is
say
it clear,
something?
everyone?
Yes, sir.
Yes, sir. Yes.
Yes, sir. Sir, if we refer the last two sessions, what we have discussed yesterday, day before yesterday and today, so that sums up the entire week 3. So we can go through this 2 weeks.
Exactly.
Yes, sir.
Yeah, I mean, it sums up all the concepts. Now you have to deal with example and all these things, but these are the main concepts which I have
Yeah,
to
I was referring to the
tell you.
concepts.
Yeah. Yeah,
Can
any
I
other
say
question you can
something?
ask? Yeah.
Sir, can
Sir,
I say something?
Yeah.
Sir, please don't angry. Can you spend some more some time for discuss about the what is span of vector, because I am got detached for few
Actually, span I will again discuss for week 4. So tomorrow is a session. I will start with span tomorrow.
In next session.
Next session. I will take that tomorrow's session.
In very short sentence, would you be able to say what is the use of a span? Because, okay, we get the range of possibilities with
basically where we are going by all this, we want to find the dimension of a vector space. Now, what is dimension? Dimension means if you want to study a bigger data, I can talk in data scientist language.
Okay.
So if you want to deal with a bigger data, now if there are some data points, if you evaluate only those data points, you can get an idea of the whole data. You will always try to find this minimal set, right?
Yes.
By looking at which you can really tell what the whole data set is.
So that we can generalize it.
maximum range. So span means basically the minimum and maximum range.
No, not really. Not really minimum maximum range. Basically, the set which can generate the whole vector space. That is the spanning set.
The data which can generalize the complete set.
So basically, we try to find the minimal set of points which can do that. Right? So that is basically the concept of basis.
Which can be.
Now, basis is the maximal spanning set. Sorry, minimal spanning set.
The minimal spanning set which gives maximum linear independence set, right?
Exactly. Basis is minimal spanning set, and once it is minimal, it is obviously maximum linear independent. I will explain that tomorrow or day after tomorrow.
In the next session.
So that's why we are interested in span.
Okay.
Is it clear?
Yeah. Thank you.
Okay. Great.
So one question: how these vectors may be helpful in data science course? Because in data science,
that I have mentioned yesterday also. Okay, just before going there to find, who are there in this session. Can you fill this form? This one, just to get who are there.
About linear dependence.
Sure, we
Sir, please can you please share the code on the chat box?
This is code. Okay, share the code in chat box.
Code not the website and code both, sir.
Okay. So how can I do that?
Sir, I want to ask a question.
Sir, you can type.
1 minute.
And you'll get a link. You can share that. Yeah.
Now where is it? Chat box, right?
Sir, general question.
1 minute.
Okay.
This is enough, no? Yeah.
Yes, sir. This will do.
Okay. So fill this form and then.
Sir, since 2 session I was waiting for a question, but the session going is so long, that's why I couldn't have.
Go ahead. Ask now.
Yeah.
Yeah, what is the question?
Sir, so activity का questions if you can see.
Activity का question solve नहीं करूँगा मैं.
Sir, solve नहीं करना.
Concept बता दिया, अब तुम try करो ना.
Sir, I don't want to solve you to do this. Just want to see a conceptual doubt.
One doubt. I have one doubt in this.
3.3 का second question था, बस आपको देखना है.
One by one. I am coming. Okay. 3 point.
Last 2 sessions.
I am taking your question. 3 point.
Yeah. 3.3 second question.
3.3 second.
Yes, sir.
This one?
Yes, sir. Second question. Yeah.
Yes, this is a good question actually.
Yes.
Just now I have discussed this.
Okay.
So there are 2 vectors, right? 3, 7, 4. Yeah. Now this question is open for everyone. Okay.
Yes,
3, 7, 4 and a vector v. They are linearly dependent. It is given. This set is linearly dependent set.
Yeah.
Under usual addition and scalar multiplication, that is obvious. Which of the following vectors are possible as a candidate for v? Now, when I have two vector,
0, 0, 0 would always be there.
0, 0, 0 is the obvious one, first one that is there, because whenever there is a 0, 0, 0 in the set, it is linear independent. Okay.
Yes, sir. And so is
what I
the
have said
B option
earlier,
as well. That is also obvious one. सर इसमें पूछना ये था कि सर 0, 0, 0 जो हम ले रहे हैं,
हाँ,
उसको हम लोग मतलब एज ए वेक्टर क्यों नहीं ले सकते हैं कि उसको इस तरह से ले रहे हैं कि वो यूजुअल एडिशन और मल्टीप्लिकेशन उसमें हुआ है. Like you are getting my point कि 0,0,0 को हम ऐसे ले रहे हैं कि वो कोई वेक्टर था जिसमें हम लोग स्केलर मल्टीप्लिकेशन किए हुए हैं, then we are getting 0,0,0.
No, this, I mean, when you are checking this, so basically what you are doing, you are finding the multiple of 374, right? The scalar multiple of 374, correct?
Yeah.
Now, what is the scalar multiplication you are taking? That depends, right?
Yeah, it depends.
If you are not taking the usual one, this may not happen.
Yes, sir. Yes, sir.
Are you getting my point?
Yeah, I'm getting your point.
That's why this is the usual.
Sir, but 0,0,0 itself could be also the linear dependent set for this vector.
If it is singleton 0,0,0, it is linearly dependent. Okay. But here the question is different. Here one vector is already given. Now my question is, what is the second vector?
3,7 means any other vector, right? If it would have been a singleton set, then we can see.
Then also it is linearly dependent.
Then
Zero
also
vector.
it is linearly dependent.
Zero vector is always linearly independent.
Always linearly dependent. But in the reflexive assignment, it is said that it must be an addition and the scalar multiplication. Then we are getting 0,0,0. It is not itself is a vector space.
I mean, yeah, the usual addition and scalar multiplication is there in my statement. It is always there.
Yeah, it is.
Because you don't know what is scalar multiplication otherwise.
Yeah.
Right? Suppose someone defined scalar multiplication like C A comma B comma C, C X comma Y comma Z as X comma Y comma 1. Right?
Yeah.
Then C into 0,0,0 is basically 0,0,1.
1.
Now that is not linearly dependent.
Yeah.
Are you getting my point?
Yeah, I'm getting it.
So that definition is
Second option is a scalar multiplication of 3,7.
Sir, one thing more. Sir,
second option is right. Scalar multiplication. So that is exactly.
हाँ, तो ये तो हो गया सर. इसमें एक चीज और.
Let Ayush finish his question, then I will take others. Okay.
Yes, sir. तो इसमें एक चीज और था कि क्या डिटरमिनेंट 0 अगर आएगा तो इससे हम इसको कंफर्म नहीं कर सकते हैं कि हाँ ये
इसमें डिटरमिनेंट निकालोगे कैसे? तो मतलब
दो ही है इसमें. 2 ही रहेगा.
3 क्रॉस 2 मैट्रिक्स बनेगा, मतलब स्क्वायर मैट्रिक्स नहीं है.
लेकिन अगर जैसे कि B option will be also correct and A option will also be correct. So if we are taking all 3.
No, that is not the question. Understand the question.
Understand. Yeah.
3,7,4 के साथ कौन सा वेक्टर लेने से लिनियरली डिपेंडेंट होगा? So 3 वेक्टर एक साथ लेने से नहीं होगा.
इसको रखेंगे, करेक्ट.
क्या ये
दो अलग से नहीं ले सकते, राइट?
1 by 1 works ना. Yeah, Ayush, you finish your question.
बहुत लोगों को क्वेश्चन है. Thank you, sir.
हाँ, तुम बोल लो.
Sir, I have a doubt in this question. Why option 4 is not correct?
You tell me why option 4 is not correct. No, option 4 is not correct. Yeah, why option 4 is correct?
Because minus 8 is there, na?
If it was 8,
it is not multiple. It is not scalar multiple. You can see.
Not 2. If you multiply it by 2, then how minus 8? It will be 8.
Okay, minus 8. Okay.
And minus 8 is the issue.
Yeah, Ayush, is your question complete?
Sir, are we supposed to just only check with the scalar multiple or anything else?
Sir, one question here only. One question.
1 minute. 1 minute. Ayush, have your question been completed? Ayush chala gaya. Probably. When someone is asking question, why you are asking in between?
Sir, one
it is really bad thing, I think.
One related question, sir.
But you can stay for the end, no? Let someone finish their question, then you can start your. Yeah, go ahead, Naveen.
Yes, sir. Question I want to ask is, they are saying that 374, V is linearly dependent. Can in some case this set be linearly independent?
If you take the last vector 6, 4, minus 8, that is linearly independent. 1, 0, 0, that is linearly independent. I mean the set which is not linearly dependent, that is linearly independent.
So this B option, like which is the scalar there? Like for example, it's for the B option. Which one is the scalar?
5 by 3.
5 by 3.
5 by 3.
So
5 by
5
3.
by 3, then it would be 0.
Huh?
Just multiply 374 by 5 by 3. You will
Multiply
get
5 by 3, 374, no?
So
That's what we are
3 by
getting.
5. I think 3 by 5.
No, 5 by 3.
5 by 3, na?
5 by 3.
If we multiply 5 by 3 with 374, what I am getting?
5, 35 by 3.
5, 35 by 3 and 20 by 3, right?
Okay.
Yes, sir. Yeah.
Is it clear?
Yes.
Sir, are we so the question I was asking was that are we supposed to only check for the scalar multiple, na? Or
so if you are given
addition
two
as well?
vectors, if you are given two vectors, what I have said, the second vector should is, our question is the second vector is lying in the spanning set of the first one, right? Span of the first one. Now, span of the first one means what? The scalar. Again, you are talking in between. This is really something bad going in this. When someone is talking, can you just please wait for a little? Yeah. So when I am saying that the second vector is lying in the span of the first vector or not, that means span of the first vector means what? Span of a single vector, right? So span of a single vector means scalar multiple of that vector, right?
Yes, yes,
so what we have to check whether the second vector is scalar multiple of the first vector or not. That is our question. That's why we are checking only for the scalar multiple. Is it clear? For two vector only. For three vector it will not work, as I have shown.
Yes, sir. For three vectors, we'll have to also check
exactly
addition
check for the span of the first two.
First two addition after finding the linear combination of both.
Exactly. Exactly. Yeah. Next, any question?
Yeah, I have a question, but it is not related. It is related to the last session on which you helped understand vector space. Pardon me if you had already covered that. Probably I got lost in the entire thing. Essentially, if you define a vector space, if any problem is defining vector space and says, okay, addition is this kind of addition and multiplication is this kind of a multiplication. So after checking out the addition and the multiplication, should we go ahead for the associative commutative laws and everything and check everything?
Yeah, right.
Okay.
You have to check all the axioms.
All the axioms, is it? Okay.
First check whether the addition and scalar multiplication is making sense in there. That means they are closed or not. That is the first thing you have to check. Then you go ahead with the axioms and keep the order of the axiom. That will be better because that ordering is made in such a way that if one fails at certain stage, you don't have to check further, right? And there is a possibility that the stage is earlier.
Okay. Because I seem to be making mistakes in that area, so I just wanted to check. Thank you.
Okay, great.
Sir, can I ask?
Yeah,
actually, sir, my question is that if I only follow the single process in R2 or R3, whatever may be, I just calculate the determinant and after that I decide that it is a linear independent or dependent, then it will be okay now. If I don't follow any other process, only this process.
So the problem is, if in R2 you don't have two vector, or in R3 you don't have three vector, then you cannot calculate the determinant, right? Because it will not form a square matrix, correct?
Okay.
So the first thing, remember, if in R2 there are more than two vector, then you directly write linearly dependent. Okay. In R3 there are more than three vectors, then nothing to check, linearly dependent. Okay.
Okay, if I get the proper equation, then I can solve. Otherwise, I will follow the.
See, you don't have to. I don't know you are getting it or not.
I want to be more precise that which process I should follow for checking the linearity.
So that is why I have written these last two pages. If a set contains in R2, if a set contains more than two vector, then nothing to check. Directly write linearly dependent. Okay. If a set in R3 contains more than three vector, then again linearly dependent. So only thing
This is
remain,
clear.
if in R2, who is talking now?
I am I want to send the same question. Suppose we don't have we have two vectors in R3. Then what should we do? What should be the right approach?
So I am telling that. You listen first properly, then again if you have doubt, then you can ask. Okay. So more than two vector in R2 you don't have to check. So what are the remaining cases? One vector or two vector, right?
Yes.
So what if one vector is given and that is non-zero vector? Then it is obviously linearly independent, right?
Yes.
Any singleton set, singleton vector, non-zero vector is linearly independent, right?
Okay.
So remaining case is only two vector that you can write by determinant. So in R2 there is nothing much to worry about, right? Clear? Now come to R3. More than 3 you are done, linearly dependent. So what are the remaining cases? 1, 2 and 3. Correct?
Okay.
When one vector, again if it is non-zero vector, then linearly independent. Nothing to do. 3 vector you can calculate with determinant, right?
Okay.
So only remaining case is this one. In R2, R3 there are two vector. Okay. Now in two vector, what I have said, if there are two vector, the second vector must be scalar multiple of the first vector. If it is linearly dependent. If linearly dependent, then second vector must be scalar multiple of the other.
Actually, we have to prepare a flow chart that which process we should.
Actually, you don't require. I mean, this is very simplification I have done. Do you have still have doubt in this? You can tell me frankly. Then I have to change something in my teaching. Maybe.
Once she will go through PDF, she will.
It is quite clear.
Okay.
Just remember in which vector space you are working. Okay, R2 or R3. Mainly these two will come. Over R2 and R4 and R5 we are not dealing with. So if it is in R2, if there are more than two vectors, then it is linearly dependent. If it is singleton vector and that is non-zero, then linearly independent. And for the two vector case, when in R2 we are dealing with two vectors, then check with determinant. Okay. In R3 again more than three vector linearly dependent. One vector, if it is non-zero, linearly independent. Three vector, check with determinant. For two vector, one vector must be scalar multiple of the other. That is the. So basically, few cases are not there. Okay. If you forget everything in the exam, write the equation and solve. That is the last way.
Sir, is there any eligibility criteria for quiz 1?
Assignment submission? No, not for quiz 1, I think.
Like term 1, there is a criteria.
No.
40% of.
That is for the end term. In term there is, I think, 9 assignments should be there or 8 assignments. I forgot that.
Hello. I have a doubt.
Kindly upload this PDF after this session, sir, please.
I will.
So I have a doubt. It will be uploaded, please.
Krishna.
Yes.
Brijesh. Yeah.
Sir, so I have a doubt. Sir, it is not related to the vector space, and this linear independent is actually related to the matrix. And since we are at the end of the lecture, then it's a conceptual doubt. So sir, how we can draw? So can you write a 2 by 2 matrix 1 1 minus 1 and 1? So can you write it on 1 1 minus 1 and 1?
Okay. 1 1
minus 1. No, sir. 2 by 2 matrix. The matrix. Sir.
Okay.
So 1. Okay, sir. So it's 1 minus 1 1 1. Then 1 minus 1 1 and 1. So how can we draw this matrix on the graph?
What do you mean drawing a matrix on a graph?
So it's actually, I was reading, so it's actually a concept of rotation and scaling matrices.
That will be in week 7 and 8. So no, that is different. You are not drawing a matrix on a graph. you are basically taking a vector and apply this matrix. So matrix is basically corresponding to a linear transformation, and you are applying that linear transformation on the vector. Okay,
Okay,
you
so
are
it's
not
there
directly
in,
drawing a matrix on a graph.
okay, so it's there in further week.
It is there. It is linear transform after coming week 6. Okay. So there is called something called linear transformation. I mean, there is a question in assignment also like this. You can see. Okay. So this is basically matrix implementation of a linear transformation, and you can apply this linear transformation on some vector and get a new vector. So in graph, what you are seeing is basically applying a linear transformation on a vector. Okay.
Okay, sir.
Okay. Yeah. Any other doubts?
Sir, I have one doubt. Just a general doubt.
Yeah.
See, vector means it has both magnitude and direction. Why we are not talking?
Again, you are going to physics.
Okay. So that is different.
No, it has a direction. Here also.
Here also it has a direction.
Because where is your point 1, 0? Here, right?
Yeah.
So it is on this side.
Okay.
Where is 0, 1 on this side? And what is magnitude? This side. So this magnitude will become norm in your week 8 content when we are talking about inner product and norm. So inner product will take care of the direction, basically the angle between two vectors, and norm will be the magnitude. So there you can relate with that. Okay. This is actually going hand by hand, but to avoid further confusion, I am avoiding magnitude and direction.
That's it's the curiosity.
Yeah, but it is there. It is there. It is the same thing. Same thing is going on here.
Sir.
Yeah.
Sir, I have a Sir, I have a confusion. When you tell us if b by 5 minus 9 by 3, sorry, a by 3 not equals to 0, then no solution. So here is a, can you show?
Where I have written this somewhere.
We augmented matrix.
Here.
But in previous we say when 0, 0 is coming and b by 5 and minus a by 3, some values is there. So there is no solution. So
why is that? Is it?
Here I'm confused. You write it not equals
this
to 0.
Part.
No solution. Yes.
So if you have something like this, suppose there is 7 and there is 0, 0, something 9.
Yes.
Is this has a solution?
No.
Why?
We cannot find the solution to x.
No, what is the second equation coming?
Because 9 cannot be 0.
0 equal to 9, right?
Yes.
This is absurd, right?
Yeah.
So this cannot have a solution, right?
Yes.
Same thing. If this portion is non-zero, that means 0 equal to some non-zero number. So it has no solution.
Okay.
Got it, no?
Got it.
Yeah.
So when do we have the next session?
Tomorrow.
Sir?
Same time? 6 to 8?
Tomorrow I forgot. Yeah, 6. Tomorrow from 6, I think.
Sir, if a set is linearly independent, then that means if we remove anything, it will still be independent. And
you
if
tell
we
me.
add any, I think it should be.
First you tell me. Yeah.
And if we add anything, it will no longer be independent.
That may not be. I mean, even if you add anything, it can be linearly independent. So suppose I am giving an example. Okay. Suppose I have 1, 0, 0, 0, 0, 1 in R3. This is linearly independent, right?
In R3 you are saying. Okay.
This is linearly independent, right?
Okay. Now got it.
Now if I add one more vector.
0, 1, 0.
Okay. This is still linearly
So the
independent.
first one which you wrote is actually like a subset of the independent set, na? Like what is it called?
So that is the point, no? I mean, it is a linear independent set. I mean, subset of linear independent set minimum. This is linear
Like
independent. This set is linear independent,
maximum
right?
independent.
Subset of a basis. That is different case.
Okay.
Okay.
So if the okay, that is why I'm having confusion.
Yeah. So
There
as a
were
set,
options.
it is a set which is linearly independent. I can add one more vector, still it is linearly independent. Right?
Okay. But still, it should not be more than the vector. Like if it is R3, then maximum distance is
Then it
R2.
should not be more than 3. Correct.
Okay, sir. Got it. Thank you, sir.
Okay, great. Okay, should I close this now?
Yes, sir.
Yes, sir.
One second, sir. One more thing.
Asif doubt. Asif is asking question.
Sir?
Yeah.
So, like, just to summarize, we can say that whenever we have to find dependence or independence, we'll take the set of vectors, make a matrix, and see if the solution exists or not.
Asif, have you joined just now?
No, sir. I was all along. I was just watching. I was waiting to ask questions.
So always calculating determinant is not enough. That I have
No,
said,
not determinant. Like we'll try to see if any row is full zeros or something like that, or some multiples or not is
that
existing.
is also there, but I mean I have distributed the cases, right?
Make equation and then
make equation is the one thing, but if you there are still lot of things you can do.
Like you did C1, C2, you took C1,
Yeah.
C2.
If you want to leave, you can leave now. I mean, nothing is.
You were taking C1, C2 and then solving and seeing if the solution is existing or not, something like that.
That is the basically found the sketch that is going on. But if you see suppose you are in Rn, you have n plus 1 vector, then it is obviously linearly dependent. You don't have to check anything, right?
Because like I'm asking from the exercises point of view, we are given many options. Like if this is the set of vectors, I am adding this vector. Is it still dependent or is it still independent? So from that point of view, I'm asking.
Then you have to go through the definition, I think.
Because we are given like 3-4 vectors, and then we are asked like first 3 vectors, is it dependent or not? And number.
So if these 3 vectors are in R3, you can check determinant, right?
Yes, sir.
If these 3 vectors are in R2, then you don't have to check at all. You can directly write it is independent. Correct? Right. If among those 3 vectors, one is scalar multiple of another one, any one, right? Then you can write linearly dependent. These are tricks you can use.
Like
always you don't have to write the equation.
Various hints and relations could be there.
Yeah, you have to check that. I mean, that have to come from your intuition somehow.
Like even that one question which someone was asking about pi and e being there, even there also like one row was completely 0. So the pi and e was no significance, I guess.
Exactly, that's what I have said at that time.
Okay.
Yeah.
Thank
you. You don't have to need to know the value of pi and e.
God, I was waiting.
Okay.
Thank you, sir.
Sir, I have a query.
Yeah, about what? Yeah, go ahead.
Sir, can you please write?
Oh, I have to write. Okay.
Sir, just for my understanding. Sorry for that.
Okay, I thought I am going to close the sharing now. Yeah.
Only this set only 1 0 0 0 is it's already written 1 0 0 0 0 1 0 1 0. तो मेरे को इसमें बेसिकली जो प्रॉब्लम आती है वो आती है कि अगर मुझे इसको मैट्रिसेस के फॉर्म में लिखना है तो उसको मैं 1 0 0 0 0 1 और थर्ड रो में 0 1 0 लिखूंगा या इसको मैं ट्रांसपोज में लिखूंगा ये
column wise write vectors as column vector. Right, these vectors are column vector. If you want to check whether some vectors are linearly dependent or independent, right, using the determinant.
Yes, sir.
Right? So when you write this vector, you have to write it column wise because the equation is giving us that, right? See here 5 7 and 1 3. I am writing the equation, right? Okay. I have to find the solution of this equation, right? Whether C1 or C2 are 0 or not, right? So the equation I am getting when I am writing the matrix representation of this equation, what I am getting 5, 7 as the column and 1 and minus 3 as another column. So I am getting this as the
column wise लिखना है.
Yeah.
Right. Thank you, sir.
Okay. Good. Okay, so I am closing this session now. Okay.
Yes, sir. Thank you very much, sir.
Okay, sir. Thank you.
Thank you so much, sir.
Thank you.